Okay, welcome and good morning, everyone. I'm Debbie Liu, Executive Director of ESIG, and I want to welcome all of you to our first ever integrated planning workshop. So we are super grateful to Breakthrough Energy for sponsoring this workshop, and Professor Rajeev Ram is going to talk in a few minutes on what Breakthrough is doing in this space. Am I echoing? I sound like I'm echoing to me. Maybe it sounds okay to you guys. Oh, really? Oh, okay. It sounds horrible up here. Okay. So ESIG is holding this workshop in conjunction with the Global Power System Transformation Consortium, or GPST. So for all of you, integrated planning probably means different things to different ones of you. Today, we are going to focus just on the electric power sector. So I'm not going to talk about gas electric integration. We're not going to talk about hydrogen so much here, but we're going to focus in on electricity because this is a big enough challenge just looking at the electric sector. Now, the first session of the workshop is going to focus on, wow, this is really echoing a lot. The first session is going to focus on the need for planners to integrate across economic and reliability tools and data, right? So you've got your capacity expansion models, your production cost models, your frequency response, load flow, your small signal oscillation tools, right? So we need to be able to span across all those different tools and data sets and data transfers. And just so you all know, we are in the process right now of producing a guidebook of practical steps for planners to do this kind of integration across tools and data. The second session is going to focus on vertically integrated utilities. So it's going to consider integration. You've got that dimension of generation and load, right? Generation and the customer. And you've also got the dimension of, say, transmission and distribution to integrate across. So we're asking the question, is there a way to think holistically when we think about resource expansion and grid expansion together? And just for your information, we're going to be producing a thought piece on economic optimization. I put optimization in quotes there because we don't really have tools to do that across all of those dimensions. For those of you who are really interested in the topic of integrated planning, we've got a lot planned in this area for the next couple of years. We held a roundtable discussion with executives on integrated planning in May. We set up a public forum for education on this topic. We kicked off a task force that is producing that guidebook and that economic optimization thought piece. And early next year, we're going to be holding a workshop in Europe with GPST on modeling tools. And it's going to look at both open source and commercial approaches. And in our public forum, we're going to be holding a series of deep dive virtual workshops. So if you're interested in participating more, contact me and we'll get, or contact Ryan outside and we'll get you on the mailing list. And now I'd like to introduce Professor Rajeev Ram from Breakthrough Energy. Professor Ram is a professor of electrical engineering at MIT, and he was also the first program director of DOE's RIIA. And he is a partner at Breakthrough Energy Ventures, and he is going to talk now about what Breakthrough Energy is hoping to do in this space on integrated planning.
I'm going to quickly give you a little bit of background on Breakthrough Energy and then why we are interested specifically in looking at integrated system modeling. Breakthrough Energy itself is a fairly large organization. It's a network of investment funds, philanthropic programs, and policy and advocacy groups that are all interested in the clean energy transition. Our focus across the entire platform is to basically decarbonize the energy sector globally. So some of the philanthropic activities include work such as the Breakthrough Energy Fellows Program. Fellows is looking at very early career entrepreneurs who are just coming out of graduate school with a brand new idea and are kind of looking to think about how do they commercialize that technology. There's also Breakthrough Energy Ventures, which is much more traditional venture fund, but basically focused on investing in technologies that at scale basically reduce primary energy emission, greenhouse gas emissions by about 0.5 gigaton. There's policy and advocacy groups, which we'll talk a little bit more about, both in the United States and in Europe, but are starting to expand globally. There's Breakthrough Energy Sciences, which is very focused on providing tools as primarily open source tools across several different sectors that we basically focus on. So we kind of look at ventures as a place to start. So Breakthrough Energy Ventures has now been around for about 7 years, invested in a couple of things that are electricity oriented. So we have venture investments in the electricity storage space, both conventional storage as batteries such as ESS, long duration grid storage, as well as thermal storage. We've got several investments that are looking at generation. So kind of near-term generation, geothermal, wind, solar, but also looking at long-term investments in technologies such as fusion. We have specific investments that are very focused on the grid. So both in grid management, companies like Equilibrium, React, as well as hardware for things like reconductoring, TS conductors, as an example of one of our companies. And then we are looking also at new loads, right? So a lot of the technologies are basically to decarbonize other sectors of the economy, such as steel, cement, and these are examples that basically kind of give you a picture of this. So the reason that one of the reasons we're really interested in thinking about grid modeling, integrated system planning, is that we care very much about how to bring these new technologies and integrate them onto the grid. We also have some insight on how to model future loads, right? Because we are basically bringing these companies into scale. In addition to the work that's on ventures, there's also a policy and advocacy group. So the policy and advocacy group is very focused on how to reduce the green premium. And so some of the work that it's done, it's basically within the platform itself, it's really led a lot of the grants on modeling. And one of my favorite examples is actually this work that was basically being supported by Zero Lab and Evolved Energy to generate impact estimates using modeling on the electricity grid and in the energy sector more broadly for specific pieces of the IRA as the legislation was actually being considered. So as different elements of the legislation were being considered, there were impact assessments that were coming out in real time that were helping kind of guide the way to think about these problems. And we're not just focused in the United States. So Net Zero World is an example of advocacy that we've done globally, kind of bringing together at the level of ministers, coordinated efforts to basically think about decarbonization planning in different parts of the developing world. So this is an example of the policy and advocacy group. Almost all of this work is philanthropically funded through grant mechanisms. There's also another element of the philanthropic effort has basically been Breakthrough Energy Sciences. And one example that's relevant to this discussion is like an open data set for transmission. So several years ago, we basically published and is available on Zenodo and GitHub, an open network model for transmission in the United States. It basically also has high temporal resolution information for demand, for wind, for solar, and anyone basically has access to this data set. We understand that there's several groups who are basically starting to incorporate this in their US model planning. So the Pipes of USA, for example, is kind of utilizing this data set. There are a few commercial entities that are free to basically also take advantage of this open data set. So this is a little bit of background for Breakthrough Energy, but recently we've just launched the Breakthrough Energy Grid Modeling Initiative, which is launched earlier in the summertime. So this initiative is specifically motivated to support integrated system modeling. And so the way we look at this space is we've been kind of looking at grid modeling across different spatial and temporal dimensions and kind of recognizing that over the last 50 years that most of generation has been dispatchable, most generation has been connected to the transmission grid. There's been significant inertia historically onto the grid to kind of stabilize short-term variability. Load variation was load growth was relatively slow. Variation was relatively predictable, and there was minimal storage on the system, relatively small cross-sector coupling. And as a result, it was basically possible to kind of silo the different aspects of modeling, right? We could basically separate out thinking about transmission and power flow. We could basically think about short-term stability separately from basically looking at capacity expansion. We could basically kind of separate out consideration of the distribution grid from thinking about transmission at all. And of course, like this has consequences. It basically means that it's hard to come up with a realistic analysis of storage or transmission as a reliability asset, because you're specifically kind of separating out these kinds of modeling. Of course, like the grid that we're hoping to all build here is a little bit harder to model, right? So there's lots of intermittent generation, lots of distributed generation, so we can't easily separate out that kind of co-optimization. The inertia on the grid is basically is being reduced, so basically means the dynamics are faster, stronger. Transmission pathways depend on like the weather patterns and the time of day. There's of course, like as we're electrifying other parts of the economy, we're seeing like load growth in a way that we haven't seen in a few decades. And we're basically seeing large amounts of storage basically being added to the utility grid. And so the tools that are needed to be able to do planning and reliability that can accurately assess this kind of multi-time horizon optimization basically need to be developed. And of course, part of that decarbonization is seeing significant cross-sector coupling. And as a result, this framework that has evolved over the last 50 years, where we can sort of separate out all these different pieces of the modeling pie basically don't seem to really work as we go forward. So we are really trying to figure out, how do we support integrated system modeling? How do we make it easier to kind of think about dynamics and reliability while you're kind of doing a capacity expansion model? How do we make sure that you're thinking about co-optimization of renewables, a renewable portfolio across transmission and distribution assets? And so as a place to start, right, in this grand scheme of like thinking about integrated system modeling, we are kind of looking at 4 particular parts of looking at capacity expansion, production cost modeling, resource adequacy, and power flow, and how do we basically connect all these pieces together in an effective way. So we've been talking to various stakeholders along the space. So international organizations, national organizations, regional, local, and individuals like developers, trying to figure out what their needs are. What part of this space do they basically focus on? And where we are at this point within Breakthrough Energy is we've made a commitment to kind of support the meta tools, to not support the development of a particular capacity expansion model or a particular EMT or reliability assessment tool, but make it easier to do co-simulation, to be able to pass data between these tools. And so we are focused on developing and supporting an ecosystem that has better linkage tools, so some open source model management software that lets you basically pass data from one modeling framework to another. Cloud hosting capabilities. We want to help people migrate the tool sets that they have onto a cloud platform so that these larger scale, higher resolution simulations can be done done feasibly. We want to help with data curation. There are lots of open data sets. Many of those data sets are not validated or formatted with the right kind of structure to be able to port into the relevant simulation. So we're committed to providing, helping provide and support that in the ecosystem. Of course, kind of moving this needle forward basically means providing information on benchmarking. So how do we do cross-platform validation? How do we facilitate exchange of model parameters so one group can actually validate someone else's basically modeling? And then how do we develop and support documentation on best practice guidance? Similarly, so the USPA has a lot of experience in basically communicating the results of engineering models to a broader community, all the way out to legislators to support the development of key critical pieces of legislation. So that communication of those results to support decision making is really kind of a critical piece of this. And again, our goal is to basically help support an entire ecosystem. So we are already quite far along in terms of grant making processes and different pieces of this, but we're just getting started, right? So this was announced earlier in the summertime. We are just kind of building up our organization internally, starting to basically spend dollars in this space, really trying to understand and engage with what's the right use case. And so we're excited to partner with ESIG to help us really understand how these tools, how this platform can better serve this community, how will it get used, what's the right specifications, what kind of data do you need, what needs to be open, what commercial tool sets need to be supported. Just to kind of give you like a set, like, LA 100 for us has always been like an important example of integrated system modeling, where there are opportunities to do co-optimization across transmission, distribution, to basically think about production cost modeling, capacity expansion modeling together. So again, like, our goal is not to develop the next generation of Plexos, not to generate the next generation of GE maps, but to really kind of focus on these linkage tools, make it easier to pass data across these tools, to be able to run this kind of integrated modeling platform on a cloud infrastructure that's elastic and scalable, and to basically help the ecosystem have access to data sets that are needed to populate and run these models, to benchmarks that allow you to generate confidence inside this. And so we're excited to be supporting ESIG and this workshop today, as well as a series of workshops that will happen throughout the next year and hopefully in the future, to basically kind of think about different aspects of integrated system modeling. And so with that, I'm going to turn it back over to Debbie and look forward to talking to you. So like I'm here with 3 of my other colleagues from Breakthrough Energy. We're going to be here for at least until Wednesday evening or afternoon. And so please engage with us, ask us questions, and we're kind of looking forward to that feedback from you. Thank you.
Thank you so much, Rajeev. And now I'd like to invite up the first panel. So if the panelists are here, Carlo, Jordan, Peter, Jason, Xiaoyao, and Kelsey.
Good morning. Oh, wow, you were right, Debbie. Good morning, everyone. My name is Carlo Brancucci. I work at encoord, and it's a pleasure for me to moderate this first session in the Integrated Planning Workshop. But more importantly, I'm very excited to see how much effort and focus ESIG, but also Breakthrough Energy and GPST have been putting on integrated planning. This is something that I believe is crucial for the energy sector, but especially the power sector, to transition to a cleaner, more reliable, and more affordable future. So I'm very excited to see all these initiatives, and I'm very happy today to get the honor to moderate incredible panel from 5 speakers with a lot of expertise at 5 major system operators from Europe and the United States. Today, we are going to hear from Jordan Bakke, Director of Strategic Initiatives and Assessments at MISO, from Peter Markussen, Managing Director at Energinet, the system operator of Denmark, Jason Frasier, Senior Manager of Transmission Planning at the New York ISO, Xiaoyao Zhou, Engineering Compliance Manager from the National Energy System Operator in the UK, and from Kelsey Allen, Principal Engineer at SPP. These are system operators that provide power to literally hundreds of millions of people across the US and Europe, and they've been doing a lot of work internally to improve how they plan their system and understand the trade-offs between economic and reliability metrics and objectives. And they're going to be sharing with us how their organizations have been doing so, what their challenges are, and we're going to have a really interesting discussion. This is going to be initially kicked off by Jordan, who's going to give us a presentation about how MISO is thinking about integrated planning. And he has a great presentation focusing on the renewable integration impact assessment that many of you have probably already heard about, but also more broadly about their integrated planning initiative. So with no more comments from my side, I'd love to introduce Jordan. Jordan, the floor is yours. Thank you.
Good morning. Can you hear me? Is this better than the other mic? Yeah, I think this is actually better. Less of an echo on, I spoke too soon. Maybe I'll stand over here. It's actually better here than over there. Good morning, everyone. Jordan Bakke with MISO. MISO, the Mid-Continent Independent System Operator, is a system operator in the middle of the country, hence mid-continent. So we operate across 15 states, do transmission planning, run the electricity markets, et cetera. Thanks, Carlo, for introducing me and for ESIG to invite me to the panel this morning to kick it off. I'm going to be talking about some work we're doing at MISO with 2 different case studies to try to interweave it. But starting with the question, what should we integrate? Like, what should integrated planning actually be in the first place before we kind of get to the point where we execute that? And some of the other speakers will talk about some of the work that they're doing in their respective systems. So integrated planning, the way I think about this is it's twofold. You first have to look at what does the future look like, and how do you need to set your processes up in order to plan the system. And so there's a lot of different ways you can approach integrated planning. And Rajeev, the first speaker, really talked about the complexity that we're getting into now and the way we've historically divided our various planning functions out to help alleviate or deal with some of that complexity. And I think we're broadly having this conversation right now about how to bring it all together. But bringing it all together adds a huge amount of complexity to the system. So one of the things that I think we've learned over time, and one of the observations I have, is the goal is not necessarily to bring all of your modeling functions together and to build this extremely complex new integrated planning system, but it's really to think about how the interactions, how the linkages are changing over time when we look towards the system that we expect to have over the next 5, 10, 15, 20 years. And really to plan for that new system, the new complications and the new opportunities of that in a new way, not necessarily just bringing it all together, like I said, but really to figure out where those new dependencies are. And so the way we think about it at MISO is we first think about asking some of those questions. We think about research into the future power system, research into the process of planning, and determining what functions are codependent, how they should relate to each other. Meaning, is stability model, as one of the slides earlier shows, is stability modeling something to do at the end of the process? You start with capacity expansion, you work through it in progressive levels of detail all the way to your stability modeling, or you rearrange that into a different part of the process. So integrated planning to me isn't just about merging different functions together. It's really about thinking about order of operations and how data is transitioned between your different modeling domains. And then the other side, from a practitioner standpoint, MISO has the opportunity to do a lot of research and to actually plan a power system or the high voltage transmission system over a 15-state area. So we learn from both perspectives. And when folks on the transmission planning side look at some of the pain points and the operation, the control room, look at some of the issues they're having, they can provide feedback into those that are responsible for planning the system for what considerations need to be taken, where do we need more emphasis, and what things need to be considered more so. So the question I'm going to be coming back to is, what is the right balance between these different trade-offs, between reliability of the system, between the economics of the system, between different reliability functions and different economic areas, and how do we go about figuring out where to invest their time, energy, and money to develop the process and eventually the plan for the future system. So I'm going to be using 2 case studies today. The first one, the Renewable Integration Impact Assessment, and the second one, some long-range transmission planning work to kind of relate the 2 of these together. So firstly, MISO spent several years working through something we call the Renewable Integration Impact Assessment that we published in 2021, I believe, at this point now. And the idea was to look at progressive levels of renewable integration, because that was really the thing that we saw as being the most disruptive to the way that we historically have thought about system planning. And so we looked at the system that we had started with at the beginning and added more and more wind and solar and renewable generation, and just saw how the system performed. And the idea was to go up that and look for places where the historical practice, this historical way we look at system planning as well as system operations just changed, kind of broke down, and we needed to really think about it differently. And so we've divided this up into 3 different focus areas: resource adequacy, the ability of the system to remain reliable and serve peak demand at all times, energy adequacy, the delivery of energy to where it's needed, and operating reliability, the ability to withstand severe events, and try to look at these different domains within one consistent study framework. And so, a lot of what this first session is about is like the nuts and bolts of the actual processes and tools that we use. And so I'm going to try to focus on that in these remarks. So we developed this process for our research studies. We try to bring these different domains together. And so on the left, we looked at a traditional capacity expansion and resource adequacy to say, what do we expect a system to look like in the future first, from a resource mix standpoint, and then how does it perform from an adequacy assessment standpoint? And then we developed this looping framework where we went through and looked at the operations of the system through production cost models. We looked at steady state power flow and dynamic stability considerations, and really tried to feed information back from one process to another. So we understood that how the dynamics changed. And so when we would go through and look at maybe a 20% renewable scenario, we look at the output, like what is needed to make that system solve? What do we need to have a reliable operational system in that world? And then feed some of those results back in when we look at a 30% or a different scenario. And so it's not just a single pass through the whole thing. They're really trying to provide this iteration. And the idea there is to really be able to focus in on when we see a different experience from the system, and then what types of mitigations and thus what types of planning framework do we need to actually achieve that in reality. And so we executed this study, and we learned a few different things from it. One is that as the penetration of renewables goes up, the system operations and planning gets a lot more complex. And so I think there's 2 general themes out of here. One, we expect the system, the operation of the system and the transmission needed to reliably operate the system to look different. Like the system will operate in a much different way in the future than we've traditionally seen. But that also means that the way we need to set up the planning for that system and the planning for how we operate the markets and system operations also changes around this time. And so really, these type of studies help us focus in on when we need integrated planning. It's not just a process, because the process can be set up a lot of different ways for a lot of different systems. So we have to think about, when and under which conditions we need a certain planning assumptions to hold true, and certain different types of modeling to need to come together in order to solve for the system that we want in the future, that we expect in the future. So a few examples on the right of some things we learned. The one very kind of obvious thing on the chart is the orange bar increasing. That's stability considerations in the system. And as we looked at the model, system stability became much more important as we looked at higher percentages of renewables. And the way we traditionally think about this is sort of an afterthought. We design our system and we go, is it stable? Yes, no, and we move on. And maybe we change a few things. And what we really discovered out of here is we need to put that consideration much more in the forefront of how we think about planning, and either develop some types of screening or build it directly into the system planning process, or look at just general ways to make the system more stable with increasing inverter-based resources, such as reforms to the interconnection standards or grid forming requirements, et cetera. There's multiple ways we can approach this, but the point is that we need to focus on it sooner in the process than we would have traditionally done with a traditional planning approach. So as we got through this exercise of understanding kind of how the system would look in the future, how it would perform, what are some of the reliability risks, and how do we need to think about the way we would plan for that going forward. We then moved on to something we call the long-range transmission planning process at MISO. And this is trying to put into practice some of those learnings and actually plan for the high voltage transmission network that we would need in order to see this level of renewable penetration come into fruition. And so we developed this process, which looks similar, but has a different outcome in mind, which is the eventual construction of new transmission to reliably serve the transition. And so the way we think about this is trying to develop a robust, least regrets kind of regional backbone system, kind of for a common set of needs that we see across the region. And we do that first by kind of collecting and understanding what that future would look like, and then running it through this process of really working collaboratively with people to design, like, where do we think future generation will be? What resources do we think are going to retire? What does the load look like in the future? And kind of really build that out with all the stakeholders involved in the process before we get into the modeling exercises itself. So it kind of in this new process, when we're trying to account for a lot of system change, it's important to kind of get those assumptions and think proactively about the future right at the beginning of the process. Once we did that, we then built out models, kind of economic evaluations of production cost models, reliability models. And one of the things that we learned from the previous studies is traditional reliability models look at kind of traditional views of the system. They don't look at high renewable or low renewable output times. And some of the learnings we had is that some of the most stressful system conditions are at high renewable and low load or shoulder load conditions. And we didn't look at that before. That wasn't part of our consideration in some of our reliability modeling. And so a lot of the process here and a lot of the tools aren't all that different from traditional system planning, but some of the specific cases and the specific data that feed into those models have changed quite a bit, such as the specific scenarios and snapshots and system conditions that we're looking at when we're trying to understand what is the problem and what is the solution needed to solve for that. So we go through this whole process here and develop different transmission proposals and eventually evaluate those across a suite of different tools and eventually bring those to fruition. I'll talk more about that each stage of the process in the next few slides. So I mentioned, we first need to start with a view of the system and going through and building that out, both from a capacity expansion, but also a detailed siting. So how does it actually fit into the transmission system? How is it can perform? Looking at it, I didn't mention this earlier, but one of the first things we saw as renewable resources increase is the complexity and resource adequacy increasing and kind of just shifting of the risk. And so as an organization, we've been really focused on solving that problem. I'm not going to talk too much about it today. I'm going to focus more on the transmission side of things. But really, we need to make sure we incorporate resource adequacy, energy adequacy, or system adequacy and valuation overall directly into the planning process to make sure that when we're planning a system, it actually achieves the result we want it to achieve, which is an inadequate system. So we go through these processes first, and then we look at the economic production model cases. And so this is a bit of an eye chart here, but what I wanted to show on this one specifically is there's still a variety of tools and a variety of different data used for something that seems maybe simple, like production cost modeling. So gas prices, we've seen a lot of dynamic change on that and trying to predict the future there, when we're also forecasting a lot of changes on the generation side and the load side and different patterns. So we brought in gas modeling tools along with our power system modeling tools directly into the process. We kind of work with the like I said, detailed siting and understanding the economic trade-offs that the transmission system will bring and the economic benefits they bring through this sort of modeling. We then look at the reliability evaluation, And as I said earlier, if you look at some of the words in these boxes, winter peak and average load, we think of those as kind of some of the more traditional cases, but twilight summer, that's a new word that we wouldn't have traditionally used. And so we look at specific cases and scenarios that we're evaluating. Sometimes they sound the same, but the actual data in there might look a lot different. So what is the renewable penetration level in these cases? Where are the load levels when we think about a winter peak as the winter peak loading conditions are changing over time. So really doing a lot of data analysis underneath the surface, both from the scraping the production cost models, looking at operational data and other data to develop new cases here, put forecasted generation in the models and really understand where do we need to do this evaluation in these models. So that's the linkage. These aren't necessarily fully integrated processes. We didn't take a production cost model and a power flow model and merge them together in a new tool. But we thought about what data needs to pass from one system to another system to set up a new case to evaluate when we're looking at the system reliability. So that's from a modeling perspective, and what we can do kind of when we think about bringing different tools and data together is really iterative analysis and iterative design of this and passing that through the process multiple times. And so we first did kind of a conceptual overlay of the system, looking at kind of a quick pass through some of the tools and just figuring out where do we think the transmission network needs to build out or grow out over time. We then built through feedback and through additional modeling analysis, iterated that and eventually came up with a draft that is more worthy of detailed discussion and design. Kind of went through a lot of these questions around how are we, what problems are we trying to solve? How are these different configurations solving for the problems? What technology should be used? And trying to pass those through these different kind of tools and processes and data sets that I talked about in previous slides to iterate through various transmission designs, and then ultimately end up with something that we can build and approve. And so ultimately through this process, through first asking the research questions around what the future system will look like and how we need to go through the process to design it, and then ultimately running through a system design process, and now getting to the end of here's the transmission system that is getting approved and will ultimately get built in order to enable the system evolution within the mid-continent region, or at least kind of the Midwest portion of that. And so ultimately we ended up with the largest transmission investment in the nation's history through all of this, but really trying to work through the questions and providing the evidence that something like this is needed. And so this is just a quick image of where we've ended up with this and kind of the current state of it. And that's where I'm going to leave the talk here and turn it over to the panelists. So thank you for having me, and I guess we'll hear more as Carlo asks us all questions. And audience questions will be at the end of this. So we're going to go into the panel session now, and then we can turn it over to you after that. Thank you.
Thank you. Thank you very much, Jordan. Really appreciate the presentation. We're going to move on and continue the conversation by hearing introductory remarks from all panelists. So we are going to start with Peter, and then we're going to go through everyone and end with Jordan. And everyone is going to introduce themselves and their organization and provide some initial remarks about how their organization is thinking about integrated planning, especially when thinking about the balance between economics and reliability, by answering the following questions. What types of investments does your organization plan for? That's just to put things in perspective. How is your organization evaluating economic and reliability impacts when planning transmission? Or in other words, what types of modeling and analytical studies do you run to value the economic and reliability impacts of transmission investments? And many of them are going to be using one or two slides to also inform their answers. So first, I'm going to ask Peter to share his remarks. Thank you, Peter.
Can you hear me? Oh, there it is. Thank you. Okay. Yeah, my name is Peter Markussen, and I'm from the Danish system operator Energinet, where we have the responsibility to ensure the security of supply in the Danish gas and electricity system, and we own the transmission grid as well as we also have the system operation. And so Denmark, we are a small country. It's about a mix between Connecticut and Massachusetts, so not so large a country, and we are also a transit country, so we have a lot of imports and exports of electricity. That's good to have in mind when we then show how do we work with the grid planning. And thank you very much for your presentation. See how you're doing in MISO, and you say a lot of the process and the models we have is very much the same. But I think where we have some differences, and that is what I will try to highlight here, is one on how is it that we do our analysis, where we do a very strict distinction between what is our needs in our system and what are then the solutions. And you say, well, what we then can do as solution, that's different from probably what you can do in the US, where you have a lot of focus on transmission. There we then have a larger responsibility. So when we look at solutions, then it could be on the connection agreements or the connection requirements to connect to the grid. It can also be on cooperation with other system operators in other countries, in our neighboring countries, in Germany, Norway, Sweden, and it can also be on the DSO level. Then we also have the possibility to install our own components, of course, build grid, but it could also be then on synchronous condensers, it could be on STATCOMs or other grid components. And then finally, as TSO in Denmark, we are not allowed to own any production or storage, so we're very dependent then on the supply from producers and consumers, and then we then need to develop markets. We have a European day-ahead market and intraday market, but when it then comes to the ancillary services, there we then also try to develop markets. And then, of course, if you really have a critical situation, we can do forced delivery, but it really is the very last solution to look at. So these are the possibilities we have. And when you then look at these solutions, then there is some solutions you can do in a short term, where others, they take long time. So when you look at transmission investments, it is long-term investments. But when you look at shorter market solutions or connection requirements, there we can do that much more on short term, but it might not be able to solve some of the big challenges we see and have been explained here. So what we then see as the challenges at the moment, I try to show that in what kind of analysis are we doing at the moment. And one thing is that we do our long-term development plan, sets the overall framework. Then we have our security of supply analysis, where we look at say different kinds of security of supply. It's the generation adequacy, grid adequacy, system robustness, but also on the IT security on our critical IT systems. Then we do our ancillary service outlook, where we try to look 10 years ahead, say what kind of ancillary services do we need, also to motivate investments in delivering these different types of ancillary services from the market. We are looking at IT/OT system strategy. So what kind of systems do we need in the future? What kind of models do we need? How do they speak together? How do we work with the data compliance? We are looking now also into system strength, where you see we need inertia. We see that there is challenges with the stability of the system. So how to model that? What kind of demand can we put on the suppliers, the generators? So for example, on grid forming requirements. Then we also have a lot of coordination with our neighboring countries. As mentioned, we are a small country, well connected to other countries. We have around 7 gigawatt of peak demand, but we have more than 8.5 gigawatt of interconnector capacity. So there is a lot of coordination, both with neighbors, but also in the European cooperation. And then finally, we are now also developing a grid technology strategy. So what kind of grid technologies are developing, and how can we include that in our long-term planning. So will there be new types of technology that we need to take into consideration? And then based on all these analysis, we then do the separate business cases that then needs to be approved. And we are a state-owned company. So when we do business cases, then it's based on socioeconomic analysis. And there we include security of supply values. We include also environmental values. We look at reducing curtailment, for example. And finally, we also have to say, look, how will this influence the tariff? So we take all these four criteria into consideration. And then based on that, we then can get the political approval on our business cases. So it's a complex slide. It's a complex world we live in, but yeah, we try to structure it as good as possible. And this is my suggestion, and I hope it can inspire you as well. So thank you.
Thank you very much, Peter. We are going to be taking questions later. So please, if you have any questions for any of the panelists, please write them down so you can ask them later. Okay, now we're going to hear from Jason from New York ISO.
Thanks, Carlo. Audio good? Okay, awesome. So good morning, everyone. Thank you for being here. I'm Jason Frasier, Senior Manager of Transmission Planning at the New York Independent System Operator. We plan for, operate the transmission system and power markets in New York State. We are unique in that we're a single state ISO. There's only a couple of us out there. And we have the unique benefit and drawback of only working with one PSC. So we do well with that. And a couple of facts on the New York ISO, we serve 21 million residents in New York State. We have a peak load around 32,000 megawatts in going down right now, and then about 150 terawatt hours of energy demand per year. So I know everyone wants the facts. So Carlo asked us to try to condense all of this into one slide. I did everything I could do that, and I failed. And there's a good reason for it. So, and it kind of brought me here. So the one thing you'll hear us talking about in common, other than the models and seeing some awesome flow charts, is process. I promise we're not trying to bore you. Part of what we do at ISOs across the world is process, and there's good reason for it. That's because we're really trying to dig in and pull out the nuances of the needs on the system in order to reliably serve our power demand throughout the world. We can't do that without processes in place to make sure that we're evaluating these things in the right ways. So I had to throw this up here, and I have to talk about process, but I will get to not the best flow chart, but a decent flow chart on how we integrate models. So NYISO's process, this is what we do in planning. There's kind of three main legs at the NYISO: reliability, economic, and public policy. So two of those processes I manage, but involved in all of them, because you can see there's all kinds of arrows that point back and forth to each other. So what that means is, you know, we're talking to each other, we're sharing models, we're sharing ideas with each other all the time. And there's lots of kind of tertiary or like interconnected processes that go into that too, such as interconnections. So when I say all this, one point I wanted to make as I come through all this is, one thing that's interesting with models and processes is the people really matter. So we have a lot of very good engineers that have come up through the ranks and worked on these things for quite some time. And one thing that I have noticed in my career so far is areas that are able to integrate models and integrate processes in a very effective way have a lot of people that worked across them. So being able to work in somewhere where you're learning power flow models, but then moving on through companies where you can learn production costs, reliability planning, all of those things, I think really bolsters the ability to be able to connect these models together and understand how to do it effectively. So that's my point there. There's your process map, and I'll get to this. So when I make these process flow diagrams, I'm always thinking like, how do I beat Jordan? Because he makes some really good ones. So I'm always looking and I'm like, all right, how do I make it simpler? How do I add cooler colors? But I'm not there yet. I'll get there. So here's NYISO's planning simulation framework. I only manage two of the kind of processes that incorporate capacity expansion production costs. So I have those at the middle. But power flow simulations kind of start up front in our reliability side, our model development side, and feed into the processes that I manage that use these tools. And then on the output side, you see reliability. Reliability is very important, but I don't manage it, so I don't want to go too deep into that one right now. But as you can see, we kind of start out front, and everyone's really doing this, is you have to have really good data, really good models to start with, and then feed into a process flow where we predict what the future system may look like throughout many sensitivities, scenarios. And in today's world, that future system can be very different across those sensitivities and scenarios. So we can get a very big gamut of that, and then run through where we're analyzing that system and looking for where are there potential needs and where are there potential opportunities. So a need and an opportunity are two very different things on an ISO perspective. So a reliability need is an area where you would trigger the actual need for an investment, and that would have to happen through a process at the ISO. One thing we do well is identify opportunities. So one thing Jordan hit on really well is, we talk about process, it sounds rigid, but one thing we're doing at the ISOs that's really unique is doing more of an R&D spin on these things. So you'll see a lot of studies coming out from NYISO, MISO, all the ISOs and all the utilities across the world, where we're getting creative with not only how the world looks in the future and kind of trying to cover those wide gamut of opportunities, but also laying out potential solutions that could help solve those unique challenges. So going through the full framework, you see lots of different kind of feedback loops, and that's just a nod to how integrated the models need to be able to capture the challenges that we're facing going forward. So with that, I know everyone will get the slides after, and you can really study these and tell me how to improve my process flows, but thank you all.
Thank you very much, Jason. We're now going to hear from Xiaoyao from National Energy System Operator.
Hi, good morning, everyone. I'm Xiaoyao from National Energy System Operator. So in the past, people might know we are part of the National Grid. We're National Grid ESO. So we changed our name, become an independent organization from 1st of October. So now we are National Energy System Operator. So we're not only looking after electricity system, we also do a whole sort of planning for the whole energy system, that including the gas and hydrogen and any of the energy related planning as well. As mentioned by all the panelists, so I mean, in the past few years, we've been through the huge sort of net zero transition in the GB system. So some of the, in the past, our system is around 50 gigawatt of demand, but mainly supplied by coal-fired power station and get CCGTs and nucleus. In the last 20 years, we're starting to see a huge amount of renewable generation come into the system. We see the retirement of the existing coal-fired power station as well. So one of the big milestones we achieved recently is at end of last month. So our last coal-fired station has been retired from system. So that's since industry revolution, about 184 years, the GB system is running the supply without any input from the coal-fired power station. So that's a big milestone for us. So apart from that, as I mentioned, there's more and more renewable generation coming to the system. So from our system point of view, so we have loads of the offshore wind renewable coming to the system. We have connected more than 20 gigawatt offshore to the system. And our instantaneous penetration level from IBR point of view is achieved 75%, now reaching about 80%. So some of the issues you guys have been talking about, I mean, we are facing now day-to-day operation now already. So one of the huge issues for us is around how we actually design the transmission system to cater for all these massive renewable generation connections. And the way how we approach it, I'm probably just using one of the single slides showing here about the different stages, how we actually determine what's the best time to do the transmission investment, how do we actually get in the different transmission investment options, and how to make that recommendation to our regulator to get things approved. So all the things you start from the beginning is about energy scenario. How do we actually see the future? How do we actually achieve zero carbon generation mix? So government normally setting up a really ambitious policy target to say by what time, how we're actually going to achieve zero carbon operation. And a lot of the time, this time scale get accelerated as well. As you know, that when we have a new Labour government this July, they actually accelerate our zero carbon operation for electricity system from 2035 to 2030. So this means a huge amount of work will be done to us to deliver, done to the whole industry to deliver as well. So when we're looking at the government policy, that's they clearly setting out a zero carbon target, and there'll be a department within National Grid, the National Energy System Operator, NYISO, will be looking at the target and working with industry to say, okay, what's a possible scenario could happen to lead to achieve government's target. So that normally will lead to different scenario will be developed. Every year we have a series of scenarios to say this is a possible pathway for us to achieve all this government policy. So as a part of the analysis, we also look into about resource adequacy as well to say what's additional capacity need to be in the system for us to achieve that. So all this information will be fed into that future energy scenario analysis, as the outcome will be a set of the credible scenarios could happen to help us to achieve the zero carbon target government set out. So once the scenario is fixed, then that's going to pass to another part of the NYISO to develop what the system needs looks like. That's more related to the transmission capacities across a big boundary, what sort of additional capacity will be required. That'll be linked with system stability related issue, what sort of additional system stability enhancement will be required, and linked with the voltage as well. So what is additional voltage compensation equipment will be required. So that information then passed back to our transmission owner business. So that will be a separate transmission licensees. Based on this requirement, they started looking at what's possible transmission reinforcement can be put forward to meet all this requirement what we specified. So that including the increase in transmission capacity, or that including with additional reactive capability, reactive compensation equipment in the system. So once we have different options, I have to mention that options not only coming from the existing transmission owner, is anybody in the market, if they want to provide a solution for us, they can put the option forward. So once we have all the options available, we are going to run through that cost benefit analysis. That's probably more around economic assessment. So we'll list out all the future scenarios. We have a plexus running to give you every hour dispatching value as well. Then we're looking at with and without all this additional transmission reinforcement, what's overall system cost looks like. Then after that, that becomes give us a list of optimal transmission investment solutions. So not only we're looking at cost, we're also looking at some other aspect as well, so including deliverability, also impact on the environment, impact on the the overall cost of the benefit of the consumer as well. So after that, the list has been done, that exercise has been done. So we have a full list of the recommended transmission reinforcement that normally get published annually, sent to our regulator to get them to say this is a recommendation from the system operator. Then will be down to the regulator to determine what's the right sort of investment plan for the different transmission companies. Thank you.
Thank you, Xiaoyao. Now we're going to hear from Kelsey from SPP.
Thank you, Carlo. Good morning, everyone. I'm Kelsey Allen. I'm principal engineer at Southwest Power Pool. Just a little bit about SPP. We are a regional transmission organization, operate an energy market and transmission, planned transmission across 14 states right now. We do have other services actually out in the West. So we stood up a energy imbalance market and also a resource adequacy program in the West. And most exciting for me right now going on is not only process development, but actually expanding the RTO to the West. It'll be interesting to be able to optimize systems across the interconnections. This is a very messy slide, and I knew the others were going to cover a lot of the detail. Our process at SPP is very much like MISO and the other independent system operators. So I'll try to take a little bit of a different approach. We'll see if I can add any extra value here. So I did start with our different planning processes under our transmission expansion plan. So all the transmission planning that we do at SPP. Bread and butter for me and most of my career I've spent in our regional planning process, which is our integrated transmission planning, where we look at compliance issues, reliability issues, economic, public policy, and recently started expanding our scenario planning and looking at system resiliency. So other planning processes on our floor, in the planning floor, we look at interregional planning, obviously generator interconnection, load interconnection, and transmission services. And you can see there on the right, just to point out that all these processes are very disjointed. They run in parallel. We do try to optimize across the different planning processes, but they're on different schedules, and sometimes it's very tough to do that. So diving into our ITP assessment, which is very much like what the other panelists talked about. We start out with our scoping and model development. So we're looking at a different range of futures, mostly to support economic analysis, looking at different resiliency scenarios to build in and other study assumptions in an integrated fashion. So our process, we very much work with our reliability and economic teams, work very close together. So finish out the modeling build, obviously go into the transmission assessments. We're identifying system needs. We look at the reliability criteria violations, economic congestion. One thing with SPP, we've officially integrated operational needs into the system. So we have criteria that we gather from our operational department, and they become official needs of the planning process. And then also public policy. Moving into the transmission portfolio development, obviously we have a lot of stakeholder input there to help us look at transmission reinforcements that we need for the system, go through a very robust evaluation process and a range of different portfolios to support. And then on the back end, looking at benefit metrics and customer rate impacts. And you can see the different metrics that we currently have in our planning process. We are, assessing the value of the transmission on the back end for the most part, and leveraging adjusted production cost savings, at least on the economic side, to drive transmission selection process. But we are looking to move some of these metrics up to provide more value in the project selection and portfolio development process. So short and sweet.
Thank you very much, Kelsey. We're now going to hear a few remarks also from Jordan to wrap up this initial remark section, and then we're going to get into an actual panel discussion.
Thanks, Carlo. Yeah, I was asked to kind of anchor this first question here to talk about anything that's unique at MISO that hasn't been talked about already in some of our normal planning processes. But I think it's been covered pretty well. As was just said, a lot of the ISOs have moved, at least the US ISOs have moved in a common direction, especially with support from the Federal Energy Regulatory Commission more recently, and the addition of reliability, economic, and public policy drivers as part of the transmission planning process. So there's been kind of consolidation in the major themes in transmission planning in the US, and we've all taken a different take at exactly how we've structured some of these processes, but that's probably a little bit too detailed for here. I think one of the other things that, and I think we have a question on this, I'm not going to get into too much, that we haven't talked about right now is we have these different processes and these different data sets, but we're all very highly integrated or connected to each other. So there's still a fair amount of challenge in planning across the larger seams in the United States, given the differences that we have, even though we have some common objectives. But I think we'll save that for a future question. In MISO, like I said earlier, we're really focused right now on making sure that we have the backbone infrastructure that we need in order to support the transition, as well as focused on interconnection requirements for inverter-based resources to make sure that the new assets that we have can reliably fit into that broader system. And then thirdly, in the resource adequacy space, really reforming a lot of the practices we use. So we didn't talk too much on this panel around resource adequacy. I don't think we will probably too much, but there's a lot of work that we're doing there to make sure that the actual generation system we end up with will actually be able to reliably serve the load. So really thinking about shifting the historical modeling and data practices there to look at how resources perform during times of need, rather than just on peak or some other historical system conditions, and then integrating those findings within the broader planning practices in the organization to make sure we understand these codependencies between them, as I talked about. So with that, I'll hand it over back to Carlo and we'll get into the discussion. Thank you.
Thank you, Jordan. So we've heard from everyone that traditionally the transmission planning process was originally driven by economics, and then reliability analysis sort of followed, but we've heard there is an increased need and interest to rearrange the process or to move the reliability considerations upward. And this sort of leads the first question that I would like every panelist to answer, which is, what are your main challenges to quantifying the trade-offs between economic and reliability impact when evaluating transmission investments? And if that's okay, maybe we can go in that direction. So Jason.
Yeah, thanks, Carlo. It's a good question. So from a quantification of the metrics themselves, I think you can see we have lots of really good tools, lots of very, very smart engineers working on this. So I think we have a good handle on how to actually quantify the different technical challenges and metrics that we have in our system. The main challenge I see in kind of the trade-offs is just a bit of the siloing that happens within ISOs and between both processes and tools and kind of needs. So you could see clearly on the process layout that each of those at the NYISO is fairly distinct and separate. I know there's lots of connections back and forth, lots of data sharing and communication that happens. But at the end of the day, we end up having to silo the needs into very individual kind of requirements. So when we talk about a reliability need, reliability is a reliability need, and its projects and investments are measured on how they solve that need, most effectively. Same thing goes for kind of economic needs or economic opportunities. They have to solve that individually. So, the main challenge I see is being able to move in a direction where we're holistically looking at all of the different metrics and finding projects that can solve multiple needs at once. And there's lots of work going on in this, and headed in the right direction with the FERC Order 1920. But yeah, from the NYISO's perspective, that's what I see.
Thank you. Yeah. So from NYISO's point of view, I think it's currently the main challenge is how to balance between the economic and the reliability impact, because we all know some of the reliability type of analysis is more like a snapshot. So you have a different snapshot. You're looking at a system capability, additional transmission investment to solve that transmission constraint as well. But for the economic analysis, is much more, the resolution is much higher, as I mentioned before. So you're looking at every hour, what sort of dispatching looks like. So how do you actually translate what your result you get from the reliability type of analysis into the economic analysis? So that's a big challenge for us in terms of you have to find the right balance. And so there's no way to do every hour transmission reliability type of analysis, but you want the transmission reliability analysis, that information, the result coming from that to be in the right level of detail so you can fit into the economic analysis. So that's, to me, that seems to be the biggest challenge for us.
At MISO, we've spent quite a bit of time over the last 15 years trying to design processes in order to be able to answer this question or do the trade-offs between economic and reliability investments. And so integrating economic analysis and the process to look at those things together. And then more recently trying to figure out the order of operations and the dependencies that I talked about earlier. But I think the biggest challenge we continue to have, even though we've spent a lot of time on it, is around data. And we get data from a lot of different people, different companies, different sources. They come through different systems, the tools, we use different formats. And so really making the data work, like being able to compare different data sets across the different tools and domains that we have, it's been a significant challenge that we still have yet to really fully overcome. And so even though we've really spent a lot of time merging the processes and conceptually understanding how the trade-off should be done, it can be really difficult in practice to make it work, even in a place where we've integrated some of the teams together, just because of how different, like I said, data collection and data systems are internally at the ISO. So I think that's the biggest challenge that we struggle with.
Yeah, and I think I will add to what has already been said that one of the challenges we look at also is the technology development, and not least also the development in the costs of technology. That where we have seen a very high increase in the cost for transmission lately. And on the other hand, we see a very fast reduction in the cost for storage. And one issue is how to include storage in our modeling. Because we actually don't know what's the storage level in all the batteries that we see out there, and how can we rely on that? How to include that? Where you say we used to have hydro reservoirs in our system, and are actually quite good at doing the assessment of the reservoirs. But should we do that in the same way for batteries, where we not are just looking at 1 year reservoir assessment, but now we have to do maybe an hourly assessment of what is the reservoir in our batteries? So that's one of the big questions we are struggling with at the moment. And then the other one is we are very dependent on our neighboring countries. So when they change their decision or change their system, then we also need to do a new remodeling. So we are actually continuously modeling our system, and it is quite stressful for our people in our modeling departments. And I really feel with them, because they are really under pressure in doing the modeling all the time. So I think we'll also say, if you're doing modeling, I support you. It's very important what you're doing. So.
Definitely echo everything that's been said. We experienced the same challenges. I'll go ahead and add in, I think one thing that everyone's dealing with that kind of plays into the challenges of quantification is really the increasing uncertainty on the systems. More penetration of renewables, that variable energy, higher levels of electrification, and then getting into those resiliency scenarios of those high impact, low frequency events. How do you understand when to build for issues like that? So the increasing uncertainty is definitely a challenge that feeds into all this. I think it's been said, but certainly the diverse input from stakeholders. SPP operates across 14 different states, and we are from Canada down to Texas, and definitely a diverse group of opinions and interests across that region. The other thing I'll throw in there is just it's easy to quantify benefits on the economic side. There's certainly metrics that we've set in place to monetize benefits on the reliability side, but when you look at the increasing need for resiliency planning, quantifying those reliability benefits definitely becomes difficult. Things like trying to assess a value of lost load and different stakeholders feel about that, and how do you weave that into the overall process so that you have an apples to apples comparison. The last thing, even if you can't quantify benefits of reliability monetarily, it is difficult, and you've got to find that breakpoint. Sometimes, there's a non-linear relationship between reliability and the cost of investment. So what's that point of diminishing returns as you're trying to expand the system?
Thank you all very much for your perspective. So we've heard about how complex the planning process is at these different ISOs. Professor Ram, I'm very happy that you are investing in arrows, because we just saw 10 slides with probably more than 100 arrows on them. So I think that I agree with your thought of that's the area that needs most investment right now. We heard about the challenges of integrated planning across different domains. This session is focused on models and data. So the next question is, how do you ensure data compatibility between your economic and reliability studies, or in other words, between your production cost optimization studies and your power flow simulation studies? And maybe this time we can start from that end.
Sure. Thanks, Carlo. Data is definitely a challenge. We have some internal efforts to really beef up our databases and automation to try to correlate different data sets and bring things together from economic and reliability planning. You look at different data sources and you spend a lot of time trying to do that correlation and map things together. So kind of keeping that common data set and trying to expand that and being able to leverage that in the planning processes going forward is definitely key. Even looking at operational data, SPP recently built some models trying to reflect some of the recent winter storms that impacted our system pretty heavily. So would definitely like to try to incorporate the operational modeling data too, to pull that into planning. As far as kind of the process, we really look at trying to do some co-development of our scopes of work. So making sure that our economic and reliability scenarios are matching up. We have a lot of work in coordination of model development as well, not just the data inputs, but building the models. We actually have a process where we take snapshots from our production cost models and take those and build reliability models off them. That is not an easy task. And then obviously cross validation of results and trying to co-optimize is also difficult.
Yeah, it is a big challenge, and a few years ago, one of my colleagues made an assessment on how much time he used on data and on analysis when he did an analysis of the system. And actually, he found out that he used 70% of his time on looking at data and making sure that he had the correct data, and then 30% of actually doing the analysis and come up with the decision. And I met him the other day and asked him again, and he said, well, maybe it's a bit better, but still we use a lot of time on data. I will try to give then an organizational view of it, because we always have a discussion on, should the responsibility of the data be in the modeling department, or should it be with those that are collecting the data, or should we have a separate organization that then handles the data? And you say at the moment we actually have a mix of it, and I think that might not be recommendable, because you need someone that actually have the responsibility for the data, so that you as an analyst don't have to go to a lot of different departments to try to find the right data. So it is a challenge, and I think it's important also to look at how do you organize it. So I think that would be my input.
Yeah, I completely agree with the previous two speakers. MISO's perspective is very similar. I would actually say if you're spending only 70% of your time on data, that's a big improvement from some of the experiences that I've personally had on it. So you're doing pretty good. Pat yourself in the back. In addition to what was said, kind of common platforming or common technology in order to move data around has been one of the areas we've been investing in lately, trying to bring the data itself onto a common system. Oftentimes that means shifting a lot of that information into the cloud in order for us to just even be able to move data from one tool to another. We've traditionally tried to move it, design like translation tools from one system to another, but just having a common data repository helps out for a lot of different use cases, both on the actual planning practices, but also the research and other things that need to get done within the organization. So that's where we've been focused on a bit. The other thing is around data collection, creating new ways, both new tools as well as new kind of standards internally to collect data from our members and from kind of the outside world and bring those into the systems for use into multiple different processes, trying to eliminate some of the silos as it relates to data itself.
Thank you. I think I agree with all that. Apart from that, one of the aspects I try to emphasize as well is around operationally how we actually going to do our studies, and sometimes it's quite different to the planning studies. I mean, so you can see actually it's quite there's some discrepancy in terms of what we identify that the issue in the planning stage, but when we move to the operational, actually is quite different. So we have to create this linkage between how the operation people talking to the planning people, making sure that all the assumptions we're making in the planning stage should be some kind of take into consideration of what happened in the real system as well. Thank you.
Thank you. So a couple points to make. One is I absolutely agree with the notion of having a centralized department and several individuals focused on collecting, keeping that data in a central place that everyone else throughout the company can access at any time. At the same time, it's important that those individuals are working with departments that are using the data, because it's hard to tell if your data is good, if it's compatible across many different tools, if you don't have individuals who have actually used it before. So having that connection, and I spoke earlier about the importance, at least on my opinion, to have engineers that have rotated through your company and have felt the different departments and worked through the different tools. And last point is, I remember, being within an ISO or a system operator, we have the fortunate advantage of having access to the source data. So I remember being on the outside looking in and being like, I wish I had all that awesome data that the ISOs have to make my models the best. But, on the outside, we do our best to get the data that we can share out there. But fortunately, on the inside, we have that source data and we can really leverage that.
Thank you all so much. And I completely agree with your general comments about the need to having some standardized data format or department in charge of standardizing and collecting and sharing the data, but also completely agree with the need to ensure that the data people have the level of expertise necessary. And that's probably one of the biggest challenges, because of this data is used by different languages, and speaking multiple languages is complicated, and translating from one another is even harder. So this brings to the next question, which is, you've already talked a little bit about this during your initial remarks. And you talked about the challenges of integrating different planning processes and across different teams. So how do you enable that coordination? And in other words, what is your recommendation for other system operators or other maybe even utilities that have different planning functions? How would you recommend they coordinate between economic and reliability planning processes and or teams based on what you are doing at your system operator and based on your experience? And maybe this time we can start with you, Xiaoyao.
Yeah, that certainly is a very good question. I mean, from national energy system operator point of view, what we tend to do is that when we're doing all these annual big exercises, we have a clearly laid out process and the structure in place. And so we get the people from the different department, but everybody knows for the different critical process steps, what's input and what's output will be required, what different data quality will be required, what sort of data source will be required. By doing that, we hope that hopefully that we can improve the coordination between the different key steps and to achieve the desirable outcome.
Thank you. I think for us, the process answer is to make sure that you have those arrows, right? So make sure your production cost model or economic models have some connection to reliability models. So go over, make sure your resource adequacy checks out, feedback, and go through the loop. So having that established in place is very important and kind of a key part. But I will say we've had, one, and I keep saying the same answer, I know. We had one reliability engineer move over to the economic side and vice versa. And I mean, it made a world difference. So you have your paper answer and then you have an answer on how to actually make it happen. And once that happened, you see the teams working together way better and making sure that the data checks out, the models make sense, the results make sense. So we've had a lot of luck with that, and we really like to foster that environment.
I'll touch on the themes of, I guess, common goals and organizational structure. So from a goal perspective, MISO really focuses on what we call value-based planning, or lowest cost of delivered energy to the end customer. And what that means, I think, to this question around economic and reliability planning is both processes or both groups have the same ultimate objective of delivering reliable power and delivering affordable power to the end customers that we ultimately serve. And they're looking at it from two different perspectives. They have the same goal. And so when they're trying to make trade-offs, they're thinking about it in the same way. And I think that's important. Otherwise, you create friction in the process by having reliability compete with cost, rather than have a kind of a common goal that both groups would focus on. And then secondly, from an organizational structure standpoint, having the various teams that are responsible for different parts of the planning process report up through a common area helps with that internal trade-off that often happens when you're trying to make some of these decisions and develop the processes and go through it. So I think just commonality and kind of clear points of decision making.
Yeah, and to add to that, I think in this coordination, that there is also a question of different cultures. So if you are talking to engineers or economics or the management or even political scientists that are looking at the regulation. So it is about understanding the different criteria that you have when you look at either the economic business case or the reliability, but also on, the political objective being green transition, CO2 neutral energy system, or being able to actually connect new solar farms or wind farms, or being able to deliver affordable electricity. And I sometimes say that having these cultures speaking together, then engineers, they say everything is possible, and you always find a technical solution that is possible. And then you need to reduce the number of possibilities by looking at the economics, and then you start looking at the business case. But in the end, it's often about politics. So, but it's actually the overall policy objective, because when you take a decision, then you have the technology, you have the economics, you have your organization, but in the end, it is a decision that is based on what is the policy you want to achieve. And that's important, that everybody knows what are the different technology, economic, but also the political objectives that you want to achieve.
I'll focus on more about organizational structure. SPP definitely had some siloed processes in the past, siloed teams. We've done a lot of work to try to break down those walls and foster a spirit of collaboration across the different planning groups on the floor. So much so that for our regional planning processes, we ended up actually combining our reliability and economic teams. And I think, Jason mentioned a couple of times about cross training. We've basically forced that combining those two teams, and so those engineers get a lot of experience on both sides. It is a lot to learn, but I think it's very, very valuable in the end. On the stakeholder side too, coordination between the different expertise in the stakeholder arena. I've noticed more and more that our stakeholders that are focused on our technical working groups that are focused on economic studies or reliability planning. We've been having more and more joint meetings and trying to foster collaboration there as well. From a study perspective, I had to throw this in there. Coordination across different groups. One of the big projects I'm involved in right now is consolidating some of our planning processes. So not just the regional planning, looking at economics and reliability, but some of the other services that we provide as an RTO. Right now, our biggest effort is actually trying to merge our generator interconnection process officially in with our regional planning process and get those customers in the mix. Try to speed up queues and have more bring more data quality and customer expertise to the planning process as well.
Thank you all so much. And it's clear to me that one way to enable the coordination is through process, but also through communication and through people. And I think ESIG has done an amazing job to bring people from different domains into one room. And I just want to do a very quick exercise. Please raise your hand if you are involved in economic planning. And now please raise your hand if you're involved in reliability planning. I don't think there is many other gatherings where there is such a fair balance between economic and reliability planning as this room right now. So I just want to give a shout out to ESIG for bringing all of us together when we come from very different backgrounds and very different planning domains. So thank you, Debbie and Charlie and the whole ESIG team. And this sort of leads to the final question I have for the panel, and then I would like to open this to the whole audience to ask your questions. How do you all collaborate with other system operators as well as other organizations, including the planning software vendors that you use for your economic and reliability planning to advance your integrated planning process? Maybe this time we can start with Jordan.
Somehow I was hoping that being in the middle would alleviate me from starting, but no luck here. A few thoughts, I guess, to start this off. One on the planning front or the other system operators. So, sounds quiet. There we go. Trying to find common goals, I think is the most important thing. We can develop all kinds of different processes, but if we don't kind of share the common goals for what we're trying to do, it won't work very well. So, MISO and SPP, we're sitting next to each other at the same table, but we also have a cross-border transmission planning work that we've been doing for a couple different years, and having a common goal allows us to innovate and develop new ways to figure out how to get the transmission needed. On the software vendor side and other side, I think conferences like this allow us the voice to speak out to a lot of different people and point out some of the challenges that we're facing. We directly work with a very wide variety of research institutions and software vendors to look at what are some of the new state-of-the-art methods out there, kind of how are other people approaching this, these different challenges, experience sharing that we get out of these type of groups. So kind of just continually learning through all this and being in this together, I think, is the best way to collaborate. Where do you want to go?
Yeah, we have a close cooperation with other system operators in both Europe, but also in our neighboring countries. And you say there is a lot of dialogue on how to use the different models. But then when it comes to do the modeling together, And again, sharing the data, there you run into a question of IT security, and can you share data with other countries, and how to improve all those processes. So that is where there is a challenge. We are try to developing an integrated grid model for both the Nordic countries, but also for Europe, and it takes time to do that. And when I say time, it's maybe 5-10 years before you actually really have a good model. So yes, very good cooperation on the software and on the model tools, but you say that the models are not better than your data. So
definitely echo comments from Jordan and Peter. I don't know that I have a whole lot to add. I mean, SPP tries to get involved in different research groups, and groups like ESIG participate in development of methodologies and looking at different studies. It's definitely fun being the guinea pig system for a lot of the work that's going on. We've been involved in a couple of different efforts recently where we've offered up our data to do analysis on our system. I think definitely increasing focus on interregional planning. Jordan mentioned common goals. I think a big success for SPP and MISO was the joint targeted interconnection queue study that we did that goes beyond our typical coordinated system planning processes. On the vendor side, I think definitely giving continued feedback. I think a lot of the vendors are certainly being more innovative nowadays, but continuing to work with the vendors and lay out the needs of our companies is definitely something to keep going.
Yeah. So from NYISO point of view, we definitely see a huge benefit in terms of the collaboration with others in the industry, especially in system operator. Because one of our experience is that if we just focus on an individual problem, when we go to talk to some vendors, they might find out that maybe the sort of market might be too small for them to do something specific for the NYISO. But if we can work with other system operator together, identify the common issue, that when we go to the vendor, that's going to be much easier conversation to have. Thank you.
Thank you. So we do have several both formalized and kind of not formalized processes where we work with other ISOs. So in the Northeast, we have the Joint Interregional Planning Collaborative, and that's a very formalized kind of public process. But we talk to each other, right? So we have a couple efforts where we're actually talking about this specific, like, how are you doing with your modeling? What improvements have you made? How can we share ideas and methods? So we definitely do that. When it comes to the software vendors, it's absolutely a two-way relationship. The system is changing so fast that the models and the software has to keep up. So there's a varying degree of that ability amongst vendors. The vendors we're working with, absolutely two-way. We're asking for things all the time, improvements, and we're doing workarounds all the time too, to make sure we are modeling and simulating the system in a way we need to. So with that one, it's just you have to be open to it, and you have to set the time aside in the development time for your tools to be able to change quickly. For the vendors we don't work with, I will say, ISOs are open and transparent, right? When we go out and present our results on economic planning, reliability planning, public policy planning, you'll hear us talk about what we're doing with the models. So if we had to do a workaround, if we had to make an improvement, or if everything's just working great, you're probably going to hear it. So I do, would invite everyone to look at the stakeholder processes that we have, follow along with what we're doing, and there's a lot to learn there.
Thank you all so much for a great panel. We'd like now to invite people from the audience to ask questions. Please share questions either for the whole panel or for any individual panelist. I'll ask you to come up to the mics. There is one right there and one right there. Please state your name and organization before you ask your question.
That's an intimidating approach. I'm Clayton Barrows from NREL. I have a question for Xiaoyao and Kelsey. I think Xiaoyao, you mentioned early on that the difficulty of running multiple planning case or reliability cases, and that being a bottleneck of how many reliability cases you can evaluate. And Kelsey, you mentioned the difficulty with actually producing those reliability cases, assuming that's from like a commitment solution and translating that into an AC power flow that converges and everything like that. Is that the same problem, or are you speaking specifically to the evaluation and the actual running of the AC power flow and the contingency and stability and so on and so forth? And you're speaking to the engineer adjusting the case to be able to converge, or are you actually just talking about the same problem?
Yeah, so I'm not sure we're talking about same problem. I try to explain what I actually means. I mean, because we have a fairly time limited window to do all the analysis every year. But in terms of how we actually set up the studies, we're looking at a different sort of snapshot of the different time of the scenario or different time of the system conditions. So we try to using that just a big when we create the when we produce the output of that, we try to use that to fit into the economic model. Sometimes my worry is that the reliability study we carried out maybe only covers a limited scenario. So whether that will be a good representation to be used for the economic analysis, this is a question about that. So that's what I'm saying. But I found that it's quite difficult to run large volume of the reliability type of analysis because of the time constraint, because of the tools capability.
Yeah, I would agree just with the general concept that you know, it's difficult to run multiple different scenarios and cover your bases. I think you know, what we do is still looking at different snapshots. I guess SPP kind of goes the other way, where we're starting with our production cost models and trying to feed all that data into the reliability power flow. It's certainly challenging trying to go from a DC solution to an AC solution under the same data set.
I was going to take a shot at this too, I guess. So one of the things that we looked at a while ago, and kind of my inclination was to actually pass the production cost case or snapshot into the reliability model. And you mentioned a lot of the challenges that you have when you try to do that with data conversion and convergence of the model, and they're looking at things differently, and so you have to make a lot of assumptions in order to get it to work. But the other thing we discovered is that there isn't really any individual hour or snapshot from the production cost model that's really representative of the reliability risk on the system. And so we focused now more on a statistical analysis of the production cost output and kind of passing a statistical representation to the reliability models to look at like a type of condition that for more analysis rather than an actual snapshot from the model. So there's a loose linkage between the two of them where there's data analysis, and we kind of pass that and then build a reliability model based on it rather than an exact port over from the production cost to the reliability model.
I'm going to go out on a limb and say I think we can address the computational time for evaluating the reliability model. I think the translation is a really hard one. And then, sorry, one last question for Jordan. That complexity figure that you had that showed the increasing complexity, what was the actual metric that was in the that makes up complexity?
Yeah, so we tried to proxy it with a different cost evaluation of the various components, or the cost of increased generation needed on the recycling side, transmission reinforcement on the kind of the transmission evaluation side, and we put it all together. And at the end of the day, we didn't really want to talk about the overall cost because it's variable and whatever. So we described it as complexity. That was, but the actual like metric underneath the surface is cost.
Thanks.
Hi, my name is Charlie Phillips. I am a graduate student in electrical engineering at Iowa State University. My bachelor's is actually in meteorology, and I worked in the utility industry as a meteorologist. So my question is, with so many more renewables coming online for the system, Do you think the planning reserve margin that we used historically is becoming a little bit less relevant, especially in highly interconnected systems? So this would particularly be a question for Jordan and Kelsey, or is that not quite correct? So just wanted to get your thoughts on that.
Sure.
Yeah, I think at least in SPP, we've done a lot of work in resource adequacy over the last 3 or 4 years. Not my forte, but I do know that we're actually seeing things go up. So we're our summer planning reserve margins going up. We've been working on implementing a winter planning reserve margin, which is going to be upwards of 35-36%. And so, yeah, the integration of renewables is actually increasing the resource adequacy risk. When you get as high a level of penetration of renewables as SPP is seeing, the value of those resources, the ones that come in late just significantly drops.
Yeah, I think the traditional notion of kind of how you conceptualize resource adequacy needs to fundamentally change. And we've done a lot of reforms at MISO in order to do that over the last 5-6 years. And the central premise is trying to align resource availability with the times of need on a system, rather than think about resource adequacy in relation to the peak load conditions of the system. So we try not to even talk about percentages in relation to peak load anymore, because really trying to focus on when is the peak risk, like when's the biggest, what are the risks that you're trying to mitigate against, and what resources you need to maintain adequacy kind of within that spectrum of risk. And so we've been shifting our entire construct over away from this traditional notion, like alignment around kind of peak load and a lot of the methodology in relationship to that, to focused on the risky times of the year. And that re-baselines your whole planning reserve margin requirement. And so the kind of the numbers you think of just aren't relevant anymore when you've shifted your metric to focus on a time that's actually less than peak load. And so your reserve margins might be negative in a traditional sense when you think about it that way. So it's complicated, but I think it's necessary to really understand what you need to have an adequate system and to reform the whole process around it.
Just a very short comment. So in Denmark, we have last year we had 65% share of solar and wind in our system. And did it influence our need for reserve? Yes, it did. But it's important to make a distinction between, the balancing reserves that you need in the hour, and then the more generation adequacy over the year, where there might be only 2-3 hours during a year in the peak demand around 6 or 7 o'clock in the evening. So I'm actually not so concerned about the wind or solar forecast. I'm more concerned about, for example, the demand forecast, and also, for example, storage forecasts. So that's getting more and more important for our need for reserves. And then also when you have reserves for wind and solar, it's much more dynamic. So we have introduced dynamic reserves so that you buy reserves dependent on what does the system look like from day to day. So makes it more flexible.
Definitely agree with the challenges with energy adequacy as well. Definitely a big thing. But I think you asked also, just to wrap up your other question about the interconnectedness of systems and what impact that
being
has.
able to share resources across.
In times of stress, we definitely have operational guidelines in place to do that. But in terms of planning that way, I think I'll just say that there's a lot of regulatory and policy barriers that would have to be broken down to truly do that in the planning world.
Great. Thank you very much.
Great, thanks. I'm John Wilson with Grid Strategies, a consulting firm. And first of all, those were great answers to the last question. I really appreciate those. But on a different topic, I'm wondering if we're getting the balance right. I'm taking this up to a pretty high level between reliability and economic planning. And to use a recent example that's really been in the news a lot is PJM's capacity market auction. And we see in 1 year a consumer impact of $12 billion. And to put $12 billion in context, the entire cost of the current transmission construction backlog at PJM is $8 billion. So we are talking about enough money to save on the order of an annual power cost to all the PJM customers that could have paid for the entire transmission construction program of PJM. And much of what's being held back by that transmission construction program is generation interconnection. And there's 13 gigawatts in PJM's queue with approved generation interconnection agreements. So we're not waiting on the study process, we're waiting on the construction. And much of the construction delay is at the transmission owner's level. And it takes a while to build transmission. So I'm wondering if our overall processes that we've seen described here are maybe too fine-tuned in looking at the economics and have not been advancing projects rapidly enough, have been too careful to make sure that they are 100% locked down, guaranteed, cost-effective, reliability incentive, et cetera. Maybe we're going too slow. Thank you.
So I didn't see a question mark at the end, but I'll try. So, I mean, I will say everything that I presented is like, hey, this is today. This is what we're doing today. This is all changing, right? So we just had FERC Order 2023 interconnection processes are changing to accommodate for increasing speed and increasing number of generation projects interconnecting. So that's literally happening today. We have an open FERC order that the ISOs have not submitted compliance to yet in process changes for FERC Order 1920. I would absolutely be looking to that for seeing how the ISOs are going to change to accommodate both faster pace and drawing up and getting a more holistic view of, you know, the different metrics and how they interplay with each other. So it's probably as far as I can go with this because we didn't really get all the way there, but I do hear your question.
Even though there wasn't a question mark.
Yeah, there was no question mark.
Sorry. Yeah, just to add a little bit on the NYISO's perspective. So not only we're looking at generation side, so we're putting a lot of emphasis on the demand flexibility as well. And another element currently we're doing is that in terms of the interconnection with other countries, I mean, so that will be hugely increased our reliability of the system.
So I think implicit in the comment is this trade-off between resource adequacy and transmission planning, and kind of how do you do that trade-off? So not necessarily the trade-off between economic transmission planning, reliability transmission planning. And one of the things that we've started to explore and put forward at MISO is this analysis of kind of the resource adequacy outcomes of transmission investment, or kind of vice versa, the transmission incorporation within the resource adequacy construct, to more explicitly model and plan for that trade-off between like locational generation placement and the locational transmission build out needed. And so I think there's a lot more research and work that's needed in that specific area that hasn't really been advanced by, I guess I don't know outside of the United States, but at least in the United States, that's still very much in kind of the development phase right now. I think at least in MISO's experience, I can't speak for PJM, we've been advancing a lot of transmission infrastructure, but we're also seeing a lot of the delays on the generation side that aren't because of transmission. There are a lot of other factors that have really put pressure on the construction of resources that are leading to kind of resource adequacy challenges and then the subsequent pricing implications of that. Who knows? Right.
Well, I got a lightning question to close it. They can do yes or no for mine. So go first.
Okay then. Good morning. My name is Bruno. I'm from the Brazilian System Operator, ONS. My question is about a little about the organization structure that we talked a little about here today. So first, you confirm an information in the countries or states that you operate. The planner and the operator are the same entity. Is that correct? And I'm asking that because in Brazil, we have a somewhat different structure. The planner and the operator of the system are two different entities. So what I'd like to hear from you is what do you think of that regarding integrated planning? And from your experience, do you see any very big advantages from having the planner and the operator in the same company, in the same entity? Of course, ONS has some say in the planning, but we're only looking a short horizon ahead, only 5 years. So what do you think of that? What do you see as big advantages, pros and cons?
Well, yeah, I guess maybe historically it changes. So I think it's sometimes good to shuffle the way you are having the responsibilities. But I think what's important for us is that we can combine the different types of energy, so gas and district heating, electricity, transport, so that you do the overall analysis and that someone does that and have the deep knowledge to be able to do that. So. But then, of course, you need to do the separate planning for electricity and gas, district heating. And there, I think it's important to have it together with the system operation because they have the responsibility for the security of supply and not just in optimizing the investment to get the most value out of the investment. So.
Yeah, at least in the US, US is a big place. There's a lot of different models that are being practiced right now, but the majority of electricity demand is served by an independent system operator, 3 of which are represented up here. And in our case, the system operator is also at least the bulk system planner. The kind of distribution system planner is different. The gas planning is different. So it's not all the functions of planning are integrated, but you have the kind of the high voltage transmission operator and the high voltage transmission planning, or at least coordination functions that are linked. And I think it's helpful in the sense that you can kind of see what's going on in some of the issues and have the primary data from the operation system be able to feed directly into the planning, and kind of vice versa. Planning, you can get direct feedback from those that are operating the system as you're thinking about planning. But I think in the biggest thing is just matching the scales between kind of the area that you're operating on and the area you're planning for. So I think the biggest advancement was just regional planning rather than the actual integration of the two in my perspective. But there's a lot of different models across the US for this.
I'll try to be quick. So yeah, we have similar to Jordan. So the NYISO has both planning and operations, same building, same company. Definitely a lot of advantages, but at the same time, like I've worked on both sides and I thought they talk to each other more than they really do. So maybe it's not as big of a deal as you might think. But what I would say, so the data perspective, absolutely, we can access the data. We can check our 20-year models to make sure our benchmarks are right according to historic data, which is great. One thing the NYISO did do is recognizing that, everyone's busy on one side, everyone's busy on the other side. Should there be a group in between? And the answer is yes for us. So we made a grid transition group, and that is individuals within that group. A couple departments moved there that were kind of interlinked to begin with. But that's been really good. Actually, a manager in that group is here today, and I can introduce you. You can talk all of it. But yeah, it has people with expertise on both sides. And we're actually on the planning side getting a lot more interaction with operators and operations individuals through that group. So even like I said, I've worked on both sides and I lost touch, honestly, once I went to planning. But now with this intermediate group, it's been really effective.
Thank you.
Okay, so lightning question, and I'm Morgan Putnam from DNV. Over the last, 10 plus years, I've watched a few companies move into the cloud and make a transition that I feel like we were discussing today, Peter's comment about who should own the data and should it be an actual dedicated group, and MISO, Jordan then speaking to the fact that that's the transition underway at MISO. I suspect that each of you and your organizations can solve that individually, but my question to you today, yes or no, should you work on solving that together? Because I think that even though your processes are different, and they're very different, you can see that from the flow diagrams presented today. But I think the underlying data sets are very similar. And I think that there would be a lot of value and you would achieve a lot of efficiencies as opposed to each having to do it individually. That's my personal opinion. So I guess the question to you is, am I right or am I wrong?
I've learned to always answer that one with maybe. It depends, yeah. So I'll give a pretty good example that I agree with you that actually DNV works. So New England, NYISO New England and NYISO both have contracted with DNV to create renewable profiles on a backcast basis that I think highly benefit anyone who wants to study the New York, New England system. So kind of started with New England, we copied them and then published the same data set that is interlinked, correlated with that. And I think I've heard great feedback on that, you know, just concept. So being able to get that data, have it be common, understand what it is, has produced tremendous value. I would tend to agree with you, honestly, on having larger scale data sets that are common. It is a very difficult thing to do on a time basis, meaning that you effectively would need an entire new department that's doing that at each ISO, coordinating with each other and making sure that happens. So, you know, right now the focus is certainly making sure our data sets are accurate and solid and working through our processes. But, you know, in the future, I certainly see as interregional planning begins to pick up more and more, I think that need will start to become, you know, a reality. So.
Yeah, I guess from a MISO perspective, I'll give a maybe answer too. I think it really depends on the situation. Sometimes, you know, organizations have unique problems and you need unique solutions. And sometimes you can leverage a scale of collaboration to come together. We have examples like the, you know, an ISO consortium for market systems enhancements. We publish a lot of common data. You have all the kind of power system information commonly reported through NERC. So there's a lot of examples of kind of how we've come together, but there's also, you know, differences that we really focus on delivering to the, you know, stakeholders and customers in our region. So specific data sets and coming out of studies and stuff for that. One of the things that I think, you know, one of the things that we need here is kind of a common group or a common entity to help bring some of those together. You know, it's sometimes difficult to have that common point of reference across here. One of the groups that I work with or represent is the Eastern Interconnection Planning Collaborative. We work a lot with the national labs in providing some common data to the laboratories to do studies and then kind of pass it back for regional studies across the system or, you know, the planning coordinator community too. And so I think there's looking for the opportunities of where that common data can be developed and shared can be as much of a challenge as actually just you know, sharing the data itself.
I'll just say, agree with Jordan and Jason. My answer personally is yes, for some data sets.
One, thank you. Two, I wasn't really referring to data sets. That's a separate thing we can talk about later.
Well, I want to thank you again, Jordan, Peter, Jason, Xiaoyao, and Kelsey. Thank you very much for this panel. I'd like you all to please join me in thanking them, and we're going to start the break. Thank you so much.
Arne Olson, a V3 is going to lead the next panel, which is looking across transmission, distribution, generation, and the customer, and looking at integrated planning across all those dimensions. So come on in, sit down, and we'll start this next panel.
Okay. Is that working? Can you hear me? Yes. Yes, is that okay? Not so much? A little closer? A little closer? Okay. All right, welcome everybody to our next panel on integrated system planning. What we heard before was pretty much a top-down level. In fact, about as far up as you can get all the bulk grid transmission generation stuff from the system operators. We're going to try to get a little closer to the ground in this panel and talk more about customer interactions. We've got a few utility folks and a couple of researchers. So I'm going to start off with just a brief presentation on sort of the motivation for doing integrated system planning. I'm going to turn to our esteemed researchers who will give brief presentations on some of the work that they've done. And then our esteemed utility panelists will introduce themselves and talk about what they're doing in their organizations and their perspectives on integrated system planning. And you can see all the names on your agenda, and everyone's going to introduce themselves. So I'm not going to take the time to go through that. And I'm going to try to go really quick because I want to make sure that all of our panelists have plenty of time to say what they want to say. So I think at the start, the primary motivation for doing smart planning, which means really doing it in the integrated fashion, is because of all the money we have to invest over the next 10 to 15 to 20 years as a result of the energy transition. It's really just increasing the level of investment that's required by orders of magnitude relative to what any of us have experienced in our careers. And you can see the numbers here from various research projects that are out there. To me, this means that we as an industry need to make sure that we're doing this really smart for the benefit of our customers and not overburdening our customers with unneeded investments, making sure the investments are at the right time, at the right place, and the right investments. And I think our regulators are going to demand this of investor-owned utilities. Boards are going to demand that of their utilities to ensure all this money that we're investing is smart and it's going to good purpose. It's the right stuff. And it's really, you can't overstate just the magnitude of the investment that's going to go into this industry globally. It's going to be a huge, issue for financial markets globally over the next 20 years. I'm going to just walk through a couple of the topic areas very quickly. We didn't hear a lot about customers on the previous panel. It was very much top down. But one of the reasons why we need to do more integrated planning is because of all the stuff that's happening at the customer level. Customers increasingly want to take charge of their own energy destinies, and they increasingly have the tools to do it. They're adopting technologies that allow them to respond more flexibly, whether that's through automated control technologies, Nest thermostats, rooftop solar, and increasingly, they're going to have very flexible resources available at their premise, whether that's Tesla Powerwalls, or hopefully many customers will have 100 kilowatt-hour batteries parked in their driveways very soon. And those are going to be, very large draws on the system at sometimes, but if they can be controlled, can be a tool to help avoid and defer system investments. So customers are going to drive the need to do this type of integrated planning. But what's valuable at the customer level is going to depend very much on what the system portfolio looks like and what the market prices look like that come out of that large system portfolio. And the easiest example to see of that is just what's happened in California and the desert Southwest over the last 5 to 10 years, where this flood of large scale utility solar has really crushed daytime energy prices in the spring and increasingly into the summer and also in the fall. And that really shapes the value of what customers might do. Your rooftop solar that you put on your house, 10 years ago is now trying to inject energy into a system that might already be flooded and curtailing utility scale solar. And those heat maps there are market prices that we project over time. In California, just with the blue being negative prices increasingly taking over most of the daylight hours. We heard a lot about generation and transmission planning on the previous panel. This is another California example where about 15 years ago, I think California probably did the first one of these, where the CAISO and the CPUC kind of got together and realized that we couldn't really very effectively plan the transmission system if we didn't know where the generation was going to be. And we couldn't plan the generation if we didn't know where the transmission was going to be. So this sort of circle of analysis that has to happen to jointly plan these two systems wasn't something that Order 888 made very easy to do. The whole idea behind Order 8088 was to separate the generation and the transmission planning functions so that the system operator wouldn't tilt the scales in favor of their own resources. So California recognized the need to sort of reintegrate these processes and develop this sort of cycle where actually the state, the PUC, does the generation planning, passes the information to the CAISO, which incorporates it into its transmission planning, develops transmission pricing parameters, which then gets passed back to the capacity expansion modeling and is used to inform the next iteration of generation planning for the state. Very similar to what the ISOs are doing mostly internally in other places. So just quickly, we've been siloed in our planning. We do generation separately, we do transmission separately. Distribution is its own process. Customer programs is its own process. It's not totally true that it's siloed, but it's largely true that it's siloed. And that's one of my questions for the panelists is how siloed are you today? And we need to move to a process where this was our attempt to sort of think about how to link all these things together visually. There are lots and lots of interactions, as we'll talk about on the panel, between customers, distribution, transmission, and generation. So we need to be able to address these linkages, even though it's very, very challenging to do that given the way that we are organized as an industry. And I want to say this is not just about utilities. We heard from all the ISOs and the RTOs. There are many, many entities that have a stake in these decisions. There are many decision makers, which is one thing that makes integrated planning challenging. It's easy for us to just sit up here and think about a top-down plan as if there was somebody who had the ability to pull all the right strings in all the right places and make all those decisions as the way the model showed. The reality is a lot of these decisions are made by different entities with different economic motivations, different regulators, different jurisdictions. So how do you actually orchestrate all of these decisions across a diverse set of decision makers in a way that emulates what an optimal system plan might look like if you could do it from the top down? So with that introduction, I'm going to turn it over now to our first presentation from Paul Denholm.
Thanks, Arne. So my name is Paul Denholm. I work at the National Renewable Energy Laboratory. And a few years ago, we completed a study for the city of Los Angeles, or particularly the Los Angeles Department of Water and Power, with their goal of trying to understand the implications of getting to 100% clean energy or 100% renewable energy. So one of the things that I want to talk about here is what we did in terms of thinking about distribution-sited resources and kind of the integration of distribution-sited resources into the mix. And I'm going to do a few things that my bosses always hate when I do, which is spend more time talking about what I don't know than what I do know. But I think that's where all the interesting questions are. So just for orientation point, this is the largest municipal utility in the country. Really interesting system from a planning standpoint. They've basically 2/5 of the nation's high voltage DC lines, or at least partial ownership of that, which really well positions them to gain access to some of the really high quality wind and solar resources throughout the Southwest. So from a 100% standpoint, LA is really well positioned, at least to gain access to that. So the study at hand was really looking at focusing on 100% renewable energy. And we did a bunch of different things around understanding not only kind of the costs and those implications, but did a bunch of environmental studies, local job impacts, and then the second phase of the study was on environmental justice. So a really fun study, a really interesting study to do. I think one of the first big 100% kind of studies that looked at the utility system as a whole. And again, tried to do some of this integrated transmission and distribution planning. So this is a slide that I stole from Brian Palmatier, and I'm going to point out to Brian and Clayton and a few others because they have a lot of answers to questions that I can't answer. I'm going to point to them for some of the technical aspects. But I think one of the fun parts of this was, okay, how do we break the wall that traditionally lies between transmission and distribution? And there's a bunch of different aspects of this. I think what I want to differentiate between here is the kind of purely technical issues in terms of transmission and distribution integration, and maybe the less technical, or is it a math problem? Because one of the things that I want to point out and talk about is there have been a lot of changes and innovations that since we completed the study in terms of answering the technical questions. Traditionally, I like to say I don't really understand anything below 69 kV, and that's where this wall has been. But we need to do a better job of planning and integrating both the transmission system and the distribution system, and solving those technical issues is one part of it. But what I really want to talk about here today, more emphasize, because these are questions that I don't understand, is some of these non-technical issues. I'm gonna get into that. But highlighting the distribution parts of this particular study. So we've already seen like 12 different versions of this type of process flow, and I really don't want to belabor this point because you all know this in terms of the flow from planning your future loads and then sticking to a capacity expansion model and doing all that other stuff in terms of reliability. Some of the things that I want to highlight here is looking at the challenges of the D part of the T&D planning. So what were some of the things that we tried to do to maybe innovate around the distributed energy resource aspect? So one of them was really look at the loads from a bottom-up standpoint. And so instead of just kind of looking at historical load profiles and growing it, doing, in this case, a physics-based approach to understanding what the load profiles might be. And that gives us insights into potential opportunities for flexibility, how much of the load is flexible. Obviously, a lot of that depends on kind of market conditions. But again, understanding how building stock heating or cooling demand might change and how much of that might be flexible if you do something like install thermal storage. So I think that was one of the really fun things. Again, looking at distribution costs in terms of hosting capacity and all those other issues, and then including distributed energy resources in the capacity expansion process to understand, okay, how might customer adoption of solar and storage affect the balance of the system, what you need on the bulk system. So just to really quickly go through the load side, this was really, again, focused on this physics-based approach using NREL's ResStock and ComStock tools. Essentially, do statistical sampling of the entire building stock in the LA DWP system, and again, simulate those buildings with the retrofits that we might expect over time, and understand, again, how flexible the load might be. There's also a bunch of non-physics-based stuff, obviously things like electric vehicles and what the charging profiles of that might look like. Some of the industries, what kind of flexibility might we get out of that? Again, this bottom-up modeling was extremely difficult and time-consuming and costly, so I don't know how reproducible this is. But again, if we want to get a better understanding of how flexible loads, I think there's some value in this aspect. So just kind of thinking about, okay, what are some things that you can do beyond traditional top-down load planning? Is there anything on kind of bottom up? And again, it's a full bottom up analysis is time consuming, but what are some combinations of some bottom up and top down approaches? I'd love to know what other approaches might be taken to get a better understanding of what the flexibility of the loads might be. And then, of course, the distribution aspects. And I'm not going to go over this in detail because, again, there's real experts in the room on this. Brian Palmentier and others at NREL led a lot of this work, and I'll defer to them on kind of the technical aspects of how this is done. But again, this gets into more of the technical aspects of, okay, well, how much stuff can you put on the distribution system before you need to do certain upgrades? But again, I'd like to point out that I think the really interesting questions here are issues around, okay, well, if those costs are occurred, again, who's going to incur those costs? How are you going to charge for them? And what are the interactions between something like increased PV on the system, which might incur or defray upgrade costs compared to something like an electric vehicle? And again, what's the combination of issues such as, okay, one customer puts an electric vehicle on their house, and it kind of kicks over to needing a localized distribution system upgrade. On the other hand, their neighbor might install PV that might mitigate some of that. How are we possibly going to do kind of the cost accounting and allocation for those types of things? I think these are really interesting questions. So part of the LA 100 study was to do this kind of system-wide look at the distribution system, what upgrades are needed, where the upgrades are needed, what types of upgrades, and then again, trying to understand what the cost implications of those. I think we didn't really answer the questions that around cost allocation and who should ultimately be responsible for these. But again, this is kind of part of those non-technical questions, which I think are really interesting and potentially need to be answered as we go forward. So once you do kind of all the stuff on the front end, again, the classical capacity expansion part of this, but the biggest challenge, of course, is in this particular case, we used a model called DGen to do the distribution cited storage growth because our capacity expansion models don't have DG in them. So as we all know, capacity expansion models, fairly simple objective function in terms of minimizing overall life cycle costs with a bunch of reliability constraints. Well, that doesn't take into account how consumers interact with their power system in terms of potential adoption of distributed resources, distributed PV, distributed storage. It's basically a different objective function. It's a different set of math. And so what we tried to do is figure out, okay, what are some ways we can have those two models interact? And this is, I think, one of the more difficult non-technical aspects of this. So a little bit of an eye chart, but this is, quite frankly, an illustration of the kind of painful process that we tried to go through to understand what would the interactions be between the T&D system, the generation system, and distributed PV. And so really quickly, and Arne kind of alluded to this a little bit, this idea of there's going to be a change in value of solar. We all know this. The value of solar, the value of electricity in the middle of the day, particularly in spring, early summer, is going to go down. And that's probably going to be captured in the change in the value of solar in terms of net energy metering, regulations, tariffs, things like that. But you have to make assumptions over a multi-decade time frame of how your tariff structures are going to change. We can do kind of LMP simulations. We can do the kind of value proposition. We can do a chronological dispatch and figure out what the hour-to-hour prices are going to be. But how that translates into tariffs, that's not a technical question. That's not a math problem. That's a policy question. And it directly relates to what kind of adoption of solar, what kind of adoption of storage you're going to have. So one of the things that I'm particularly interested in on the storage aspect is going back 20 years, we first started putting this crazy wind and solar stuff on the power grid. One of the first studies, and Michael Milligan's in the room and others are in the room that have kind of went through this, don't firm individual resources. That's one of the very first things we learned about integrating wind and solar. You balance the entire system. We start having tariffs where individual storage systems are responding to individual loads. It goes back to the whole don't firm your toaster idea. We're going to potentially be firming individual solar resources, and that's not optimum from a global standpoint. So I'm really concerned about how we are going to treat distributed solar from a tariff standpoint to make sure it's providing the optimum system. So in our study, we assumed that distributed storage was essentially controlled by the grid operator, by LADWP. I don't know if that's the right assumption or not, but I don't know how to do an optimization over thousands of individual customers that are trying to firm their own individual assets. I mean, I don't want to do that because it's not optimum. So these are just kind of examples of what kinds of things we need to consider in terms of how these systems are going to be adopted, rate structure changes, how these distributed solar is going to be adopted, and other elements like that. So again, I'm just stating all the things that I don't really understand or I don't know, and I'm hoping that the panel will answer these, and I'll learn a lot today. So we did see a lot of solar adoption and storage adoption under kind of these least cost scenarios, depending on your assumptions around net energy metering. There was a large amount of both customer-sited PV and customer-sited storage. Sorry for the graphic. The top one should say customer-sited storage there. And so based on what we think human behavior might be in terms of response to kind of standard tariffs, we see a lot of this stuff adopted, which means that also increases all the issues around visibility and all that. But again, I think those are as much technical issues as kind of these social issues. So I'm really interested in, again, what we're going to all do to make sure that the system responds appropriately to these resources. So overall, I would say the I part of the integrated resource planning is really difficult because of these stuff that we're putting on the distribution side of things. I think it's worth doing because as a central supply side traditional kind of engineer, I'm always skeptical of distributed resources, but I know that I have a lot to learn, and I know I need to have maybe a little bit more open mind about the potential opportunities for cost-effective deployment of these resources. I don't know what individual people's choices are, their preferences are. There's potential to leverage the lower cost of money associated with distributed resources that is absolutely real. So even if my kind of skepticism over economy of scale kind of comes into play here, again, I don't know everything. I don't know much about a lot of things, and I just think it's really important that we kind of get this right. So I think we have a lot of work to do to get us to this truly cost optimum mix of resources. And so how we approach both getting the math right. And again, I think there's a lot of great work that's been done on this. So I'm getting more confident that we're getting to solving the math part of the integrated T&D aspect. I'm just not so sure about the non-math, more policy-oriented aspects of this to understand how we're going to do all this. So that's my kind of quick overview. And I look forward to hearing how others are solving this problem in the following presentations. Thanks.
Thank you, Paul. I always look at that LA 100 study as kind of the best example that I know of a study that does a really good job of both bulk system generation, transmission, but really all the way down to the distribution level. That's the thing that study does differently than any other one is, really detailed look, as you said, about all the stuff that's happening at the premise level. But you mentioned that that's a time-consuming activity. It felt, that study felt like it was an order of magnitude sort of more extensive than a standard IRP. It always felt like that. I don't know exactly, but I don't know. I mean, would it be your view that the utilities just need to spend a lot more money and a lot more time, doing some of that bottom-up planning, or is there something in the middle that they can do?
So we're talking about a multi-trillion-dollar system here. So spending a little bit more money on planning seems reasonable to me. I think it's just a matter of continuing the tool development to the point where we actually can do this in a timely manner. And I think, again, we've made a significant number of significant amount of progress there. Again, I was being a little bit selfish in terms of spending my time talking about the stuff that I don't understand and I want to see improvements on, because I can talk to Brian Palmentier and I can talk to Clayton and I can get answers to how greatly they've improved the technical aspects of it. I just want to really hear how we're going to solve kind of the social and policy and economic aspects of it.
I think we'll have some of that discussion within the second half of the panel. All right, Chris Clack.
Thank you. Can everyone hear me okay? So I'm Chris Clack. You may have known me as the founder and CEO of Vibrant Clean Energy. Back in March 2023, I sold the company to Pattern Energy, which is a developer. And I've gone into Pattern as the Vice President of Integrated Energy Systems Planning. And essentially what I've been trying to do at Pattern is everything that we're talking about today, which is integrated systems planning from the perspective of how does this help and how does this work when you're a developer? How do you actually use that integrated planning framework to actually improve your development skills and where to site resources? So those who are not familiar with VCE, we created a model called Wisdom, which is our main planning tool. And the idea of Wisdom is to bring together as much as possible of the energy system. And as everyone's alluded to, it's super hard and it's never complete. Someone always comes up with a new idea or a new way of thinking, which means I've constantly got a job to do, which is selfishly quite good. And so we look at it from the whole economy is interconnected in some ways. And we start with the premise that the electricity sector is the backbone, and then we spread out from there. And so in this diagram, I know there's a lot in it, but the green lines are essentially the transmission. And then there's other lines, which are different ways of moving energy around. And we look at it from this perspective because we want to bring as much detail from the system into the model as possible. But the key with Wisdom was the first part of it, which is the weather informed, because I think as we go through this process, we're going to see more and more of the weather is going to be driving the economy. And if that's true, we need more and more ways to look at the integration because there'll be more and more risk to the weather itself. So just a bit more detail on Wisdom, just because this is my sort of vantage point of the way that I look at this integrated system is we try and look at the whole continent as much as possible for this modeling. We want to do it as a high resolution as possible. There's always trade-offs with runtime and resolution. We want to include climate data, which I'm not going to touch on too much here. That's probably another difficulty that's going to come in. But we want to include in the capacity expansion portions as much of production costs and reliability as possible without being so burdened that you can't actually solve anything. So everything in bold here is things that are touched on explicitly in the model by weather. So we have the transmission power flows and planning reserves, which are related to the weather. We have the distribution planning, which is included in Wisdom. And I'll talk a little bit more about that in the panel tomorrow. And then we have the wind and solar generation, the hydro generation, as well as the line losses and the loads, which come in as well through weather dependencies. And the reason that I go on about the weather a lot is because they're not random. It's all correlated, it's all related to each other, and it's all one physics. And so as we progress forward and we have more and more renewables on the grid and we're integrating more and more, we're going to see more and more codependencies and more risks emerging from that in the modeling and then in real life. So these are like the main data sets. And I have to admit, when I first started building Wisdom, I thought the model was the most important piece. I've been humbled by the fact that it isn't. It's the data. And I think we've been striking on that quite a bit here, because as you add more data, the model doesn't get particularly more complicated, but the runtimes do. But what gets more complicated is how everything interacts with each other. So every one of these on the left-hand side are actually related to the weather in some way. Even buildable areas, we've been finding that as the weather can relate to how you can actually build on the ground and your build times as well. So if we believe that we're going to get electrification, which I do, the actual amount of energy we're going to supply is going up. So that sounds good from a planning perspective. We can add more customers and we're producing more energy. The flip side, as I just said, was that there's actually more risk because more and more of your economic output is related to your weather. But the thing that's going to keep increasingly shape the weather, which is what Paul just alluded to in the LA study, is that the weather shapes the demand. So you've got the supply being shaped by weather, and now you've got demand shaped by weather. And depending on how you model this from the bottom up, you can see these big spikes. And I like to see that these big spikes that I'm showing here were actually showed up in the LA study as well in winter. And the reason I like to show this plot is first of all, the scale of the problem. We're doubling electricity demand if we believe that we're electrifying, but also we're shifting when these pinch points happen. And what we found when we've actually modeled with the weather and the covariances of the weather is the flexibility in these time periods are actually very, very small because these are normally very cold, not very windy, not very sunny time periods. And so you can't really down dispatch the loads because you need to keep the building stock warm and you don't have any generation to go up. So it's a double-edged sword as well. Just want to relate two more things is transmission ratings and heat rates are also weather driven. They change based on what the weather is. And so we include that in our modeling. Again, you might think it's overkill, but what we're seeing is actually, we're seeing like more outages, not because there's not enough capacity, it's because the heat rates are going down in summer. And so we're not seeing as much power coming from the generators. The little thing that I will talk about with climate, just at one point on this, is that climate makes all this worse. As the climate is changing, we're making everything more difficult. And some of the studies that I've been doing with climate, for example, we'd need to produce around 9% more electricity at source just because of climate change, just to get it to the customers. So if you assume load growth is flat, we need 9% more by 2050, even just to overcome the different climate scenarios. And we also have water availability and heat rates, which again exacerbate this problem. So I won't belabor it. But if we come back to like tractable problems, so there's lots of things we can add. We simplify things in the model, like everyone has to in models. But today's issue is integrating wind and solar, and these load ones will come later. But the reason I talk about them a lot is because as planners, we should be planning ahead of what's actually going to hit the grid. So we have wind and we have these pretty maps, and we have solar, which is a pretty map, and these are long-term averages. But the thing that I don't see enough in capacity expansion models is the interannual variability of all these years of data. So this is just 8 years compared to those averages, how they differ from those averages. And so red is plus 10%, blue is minus 10%, in terms of gross capacity factors. So some years, if you pick the right year, you can look like wind's doing really well. And this is wind, by the way, sorry. And if you choose a bad year, so if you choose the first one here on top left, you do really well with wind. And if you choose the bottom right one, you do really bad with wind. And so having multiple years and having the model solve over all those years for resource adequacy is really, really important. So with all those problems, I like to sometimes try and provide some solutions. So what we've started to do, and Patton has been really generous in doing this, is we're actually releasing a data set with Catalyst Cooperative and Grid Labs, which is a county level hourly resolution capacity factors for wind and solar across the whole continent. We're starting with the 5 years from 2019 through 2023. And then beginning of next year, we're going to release the preceding 5 years. And we're going to keep releasing that every year until NOAA stops producing the high resolution rapid refresh as an operational model. It'll probably take us some time to convert to whatever new model they're going to use. But the reason we're doing this is a starting point of having a consistent data set that is across the whole continent that anyone can use for free, that is small enough to use in any capacity expansion model. The full data set is around 2 gigabytes, I believe. We provide it in multiple different data sources thanks to Catalyst. The QR code is up there for anyone that wants to go straight to the website and start downloading it and working with it. And this is the tip of the iceberg. We want to start providing temperatures and solar irradiances for looking at the load side. So this is, again, just supply side. But we need to start acting more as a community to provide data sets for everyone to use, because no single entity or person has all the answers. And we need to be able to start tackling this problem at a faster pace. And so I'll just leave it there. Thank you.
Okay, thanks, Chris. Really interesting. So I heard from Paul that we need detailed premise level data on customer adoption. We heard from Chris that we need detailed county level data on wind and solar production. So and we heard that this earlier that some of these researchers are spending 70% of their time on data, 30% on modeling. I'm sensing a theme throughout the day here. Okay, so we're going to shift into the discussion portion of our panel. So what I'm going to do is just first turn to our utility folks on the left, ask you to introduce yourself, and then talk a little bit about what your organization has been doing with respect to integrated planning. Do you have a mic over there? No. Bring this one over.
Thanks. Hi, Ken Aramaki. I'm the director of T&D and interconnection planning at Hawaiian Electric. Our company started the integrated grid planning process in 2018, and this year was so what is this? 6 years later. 6 years later. I can do math. We got approval of our first integrated grid plan, which consists of the generation, transmission, and distribution investments needed for the next 5 to 10 years.
Hi, good morning, everybody. Before I talk about me, how many of you traveled from the west side of the United States? Listen, are you guys dying right now? Like so tired and jet lagged? So you have to recognize this panel, right? We may be more articulate as the week goes on. So we're gonna just try to get through the panel today. Okay. Angie Mon Simpson, I'm from Salt River Project, or SRP. We are a public power utility located in the desert Southwest, serving about a little over a million customers in the greater Phoenix metropolitan area. We started integrated system planning conversations about 2019, actually locked about a dozen analysts in a room in 2020 for a couple months to develop a process, and then launched a public-facing integrated system plan in 2021. Happy to say our board approved our system strategies or our integrated system plan just a year ago. So we've actually been working off of that integrated system plan to try to tackle some of the big weedy issues that are happening across different disciplines at SRP.
Hey, good morning, everyone. My name's PJ Martin. I'm the Area Vice President for Modeling and Analytics at Xcel Energy. We started our integrated system planning journey a couple years ago. I was actually at ESIG in October of 2022. It was in Minnesota, so that was nice. I live in Minnesota. And was able to talk a little bit about the early stages of formation for our group. So obviously 2 years have passed. A lot has changed. Starting up ISP was, I think, critical for Xcel. I think Arne had he wanted us on a scale of 1 to 10 to talk about how integrated we were before and how integrated we are now. I would say back pre-ISP, we were probably about a 3. I was actually the Director of Resource Planning for NSP, our Upper Midwest system, for a number of years, and starting in like 2015. I think some of the earliest interactions between some of the different groups. So I was in generation planning, ran an RFP for thousands of megawatts of wind in 2016. And that was really one of the first times that we really had to start talking to our transmission group, because we were looking at the MISO queue. We were getting thousands of megawatts of wind bids. And it was like, you know, what are the upgrade costs attached to some of these different projects? Where are they in the queue cycle? Do they have generation interconnection agreements? Are they in DPP 2, 3? Where are they? So a lot of conversations there, especially on the modeling side, trying to figure out, if I'm modeling generic wind and solar, what sort of dollar per kW transmission cost do I need to attach to that wind and solar? Want to try to co-optimize the generation and transmission investment as much as possible. So definitely were some elements of it occurring in the early stages, but I can tell you, when we started up ISP 2 years ago, I had not had extensive conversations with anybody on our electric distribution or gas side, and absorbing those modeling teams into my group now, it is pretty amazing to try to change mindsets. And we were very much 5-year budget focused in both of those areas. And frankly, in electric distribution, I mean, they're almost 2-year budget focused. And then there's a bunch of placeholders in the 5-year budget beyond that. So it has, I think we'll talk about culture change at some point. I have a lot to say on that. It's been a big culture change process in Xcel. ISP in Xcel now is comprised of a little over 200 people. So we absorbed all of these groups that were in the different functional areas. So energy supply, transmission, distribution, gas, and created one group. And, you know, as folks who work with utilities know, we're not the quickest and most nimble folks in the room. So definitely have worked on the culture change piece and have some interesting stories I can share on that.
PJ, it sounds like it was really this transmission generation question that drove you to integrated system planning. Was this just internal? All your analysts looked at this and said, we don't know how much the transmission is going to cost. We need to do more integrated planning. Distribution kind of followed along behind that, or so where did the impetus come from to do this?
Sure. So good question. Alice Jackson is our senior vice president. She's my boss, senior vice president of system planning. She had previously been the president of our PSCO operating company in Colorado. So I think, again, like our regulatory groups kind of have that lens where they work across all the different areas and see all the different filings that are being requested of us in various jurisdictions. And Colorado is a very progressive state. Minnesota is also very progressive, but I think Alice had a unique vantage point where she saw distribution system plans being filed and more requirements coming from the commission, poking and prodding us to get a little bit more proactive on the distribution front. And then she also saw some of our electric resource plans in Colorado as well, where we were having to proactively build large transmission investment. The Clean Power Pathway is a big multi-billion-dollar project that we're in the process of building in Colorado, and making sure that we have that transmission available so that we can add the renewables. And then seeing the pressure on the DSP side, I think she was a big proponent of forming ISP and leads the group right now. So I think talked to a lot of her peers internally and generated some of the momentum.
And then, so Angie, I know that some of your, process came internally, but so from Salt River's perspective, how disintegrated were you on a scale of 1 to 10? And what was the driving factor behind, really a kind of what someone might think of as a sort of a reliable, maybe conservative public power utility kind of going out there and in the forefront of the industry with this innovative planning practice?
So you're asking me to air all of our dirty laundry in front of everybody. You guys aren't going to tell my boss what I say, right?
Only after it's been cleaned.
Yes, yeah. So I'd say before the ISP, we were probably in the 4 to 5 range out of 10. So it was kind of dependent upon individual relationships. So if a person had a long experience with another, like if a generation planner had an experience with a transmission planner, then that tie was pretty good, right? So very person specific. The interesting thing about it is, being siloed isn't totally bad. So the benefit of being in our sort of individual silos was that we had a lot of specialization and deep knowledge and awareness of our individual disciplines. And that's something to be really, really proud of. SRP really, we celebrate that we have high customer satisfaction, high reliability, high affordability. And so in a sense, we were on a good trajectory. The sort of issue was in 2017, we published an integrated resource plan. And at the same time, there was another group that did our corporate sustainability goals. And to be totally honest here is the sort of the catalyst of integrated system planning was those two things really pissed off a lot of people at SRP internally. And it was because as an organization that had leadership, that had deep industry expertise, those things were really setting us up for change. And in some cases, the resources that were planned were to retire coal generation for carbon emission reductions and to add renewables. And so if you were sitting on the operations desk or you are a transmission planner, your question was, how in the world are we going to be able to do that and maintain our leadership in the industry in terms of reliability and affordability? So I think it boils down to when you have silos, the problem actually occurs when each of those silos has a different objective. So we had a transmission and power system group, and their objective was to be the most reliable utility that we could. We had a finance group, and their objective was to be the most affordable utility. We had a sustainability group that was driving us, and those things were conflicting. And so when we started the ISP and through the process, we kept trying to get to balance. We don't need the perfect optimal reliability plan, the perfect optimal financial plan, the perfect optimal sustainability plan, because inherently we were going to throw off one of those other objectives. So when we started working together, it was really more about how do you strike the balance between those three to provide the best customer value.
Thank you. Super interesting. When we heard earlier from New York ISO that even at that level, those personal relationships are still important to kind of break across those silos. So super interesting that that's your experience as well. And I think what I heard from both of you too is really this relied on sort of leadership, proactive, forward-thinking leadership to help drive these organizational changes, which again is not something people necessarily think about when they think about the utility industry are proactive and forward-looking, but we are seeing examples of it here. So Ken, I'm interested in your perspective on this as well. I know there were a bunch of external factors in the case of Hawaiian Electric that drove you to this idea of having to integrate planning much earlier than maybe some of the other utilities.
Yeah, so at Hawaiian Electric, thanks for the comment. I came from more west than that. We manage and operate 5 distinct island systems. So each of the islands are planned by the same organization, but each one has its own individual plan. When we do projects, a lot of we impact communities, we impact within each island, there's microcosms of communities, and we impact each of them individually. That's where we get hung up a lot of times in executing a lot of the projects. So the integrated grid plan process started because of our discussions with stakeholders, discussions with communities. That's a large piece of what our integrated grid plan does, is it informs, it educates, and it helps provide an avenue for stakeholders and communities to provide input into the process that would have otherwise not been. Within the company, I would say that our pre-IGP, we call it IGP, pre-IGP process, we're about a 3.7, 3.78, somewhere between 3 and 4. Now, I mean, I wouldn't say we're at a 10, maybe around a 7-ish. You know, there's always room for improvement. There's still silos that do go on. You know, we are still organizationally set up in that traditional process, but we have a lot more interplay between the areas, and we try to make sure that each of the areas are having constant discussions, and everything is, you know, the plans that are developed and designed, they're all designed together. And then in the end, there's a lot of feedback loops that go back and forth. Did I even answer the question?
No, I think you did, yeah. So one thing I touched on in my presentation, I think we've heard a lot already, is just the changing nature of the supply side portfolio and how that changes the value of what you might want to do at the customer level. So are you seeing that on your systems? Do you agree with that? You know, what are you doing about it in terms of how you're sending signals to your people that are designing customer programs?
Okay, I'll go first, I guess. So one of the things that we recognized when we pulled in, so distribution, transmission, generation planning, our pricing team, our customer program team, our forecasters, our operations folks, is with the power system changing, some of the signals that we are incentivizing today, so electric vehicle charging overnight, are totally 180 degrees from where we need to be in the future. So what that has led to is really trying to understand where the value lies. So should we do time of use programs that have a super off peak and then have a conservation window from 6 to 9? So we piloted a process for that and are looking at maybe rolling that out over the next year. But we're also looking at, when you're talking about distributed energy resources, you know, the value of resource adequacy or the energy value for that is actually really, really low for SRP today. If you were talking about that from maybe a resiliency issue, or if a customer wants to do that, then you have to remove technical constraints from the ability to interconnect. And so it's hard to say for us, like, we don't see any value in it if somebody really wants to connect that, and we have to figure out how to integrate that into our system. We start to turn, I think, a little bit more to electrification programs to try to build load during the daytime hours between 9 to 3, and really align our conservation programs. Cooling load or air conditioners and weatherization are really important programs for SRP because they end up conserving during the hours where there's the most system stress. But there's also kind of an equity component. So some programmatic impacts are also aligned with, you know, customer satisfaction or low-income customers having more access and control over there. So it's, I would say, in essence, we recognize that we're going to have to send different signals. And I think that, you know, part of integrated planning is really trying to understand and be able to point to a body of work that supports that, because it's very difficult when you're interacting with a customer and you've been telling them for the last several decades, you know, do this behavior, to tell them to change that behavior is very confusing for them.
Yeah, I'll just add to that. I think particularly on the EV side, we need to get good programs in place where we can control and shift and flex EV load as much as possible. We want to avoid building generation capacity to support any impacts on net load peak from EVs. So I think that is critical. And it's even more critical now, given the influx of data center load requests that we're seeing. I remember being here 2 years ago and talking about an all of the above approach. Now more than ever, we need an all of the above approach, because we're seeing requests from thousands of megawatts of data centers across our service territory, as are lots of other utilities. It's been prominently in the news recently. And that is going to require us to like relook at the role of like natural gas, for example. When we were in a period of flat load growth, it was very much, let's add renewables, let's get the coal off the system, let's maybe replace brownfield gas sites, let's avoid greenfield gas additions as much as possible, let's not build out natural gas pipeline infrastructure as much as possible. We are at a point right now where we need to revisit those preconceptions because of the amount of load growth that we're facing. So it's going to be even more critical that we can roll out good programs where we can flex load, customer load as much as possible, because right now the data centers are not willing to flex and are pretty high load factors. So, you know, particularly on the EV side, I think, you know, home, you know, customer sided battery storage is another opportunity. Even water heaters. I have a 7 or 8 year old natural gas fired water heater in Minnesota. We have terrible hard water in Minnesota. My water heater is about to go. Recently got a quote for a hybrid heat pump water heater with the federal tax credit. It's about the same upfront capital costs as the natural gas option. That should be a no-brainer. Anybody who's looking at gas replacement right now should be switching over to a heat pump. And then we need to figure out how we design programs where we're flexing that load and ensuring it doesn't have an impact on system peak.
It sort of seems like this flexibility of load and how to harvest that using, you know, customer programs or rate design. That's kind of been the holy grail for a long time, but we've maybe had the luxury of talking about it a little bit in theory. But now, so I'll ask you, how much of this are you seeing at the customer premise? So how much are we starting to see EV adoption that's noticeable, where you're really having to now be active and go into distribution areas and do, you know, detailed planning around how many EVs you'll see? Are we seeing enough home customer storage adoption, or maybe even like industrial scale storage adoption, to where you really need to be in there with flexible signals today? Or is this still like a 5-year out problem?
I can give an example that comes to mind about all this customer program. We adopted a pilot to do a time of use. We did a time of use pilot last year. So basically during the day, because in Hawaii, we have a lot of solar. So during the day, we have a lot of generation typically. And then in the evening is when we peak. So we incentivize customers by way of time of use, right? So during the day, lowest rate, evening, highest rate. And it's pretty substantial, that delta. So there's customers now that are coming to us to like larger customers to do to store like ice generation, where they, you know, they I don't really know the mechanics of all this, but basically it's a shifting of storage resources to displace their evening peak. I recently got feedback from the operations, and it's like their feedback is, why the hell are we doing these programs? Because, you know, 99% of the time it works, but there's the days that you don't have solar, you have low. And a lot of our utility scale resources are solar plus storage. So we don't have enough stored in our own resources to manage what would now be a daytime peak. So then they run into issues with that.
Yeah, at SRP, we have, let's say, about 50,000 EVs in our service territory, about 400-ish megawatts of customer-sided or demand distributed energy resources, and about 5 to 10% has a battery tied to it. And so I'd say we're not in a spot where we can see giant benefits, but we're in a spot where we need to plan ahead, because if we assume that 5 to 6 years out, you know, is when we're going to have that solution in place, it's going to be too late, right? Anything that hits at an individual customer's values or tries to get them to change their behaviors, that has to be very carefully planned out and very carefully communicated. And I'd say that's one of the challenges of integrated system planning, is it's quite technical and complex. And then again, trying to communicate that to an individual customer in a way that resonates to them, that they think about their utility more than 3 minutes a year, is difficult, right? Is very difficult. So we have a couple of, I'd say, I can't think of the word right now. I'm blanking. In the works processes. So while we're looking at these customer programs and dispatchable and flexible loads, we also recognize that SRP has to upgrade our customer information system. And to be able to push these changes to individual meters is probably 3 to 4 years out to be able to do that. So we're actually trying to look at if you could cite some of the storage on the distribution system on our 12 kV system, could you essentially try to mirror what economies of scale would do that at SRP's level and maybe not necessarily rely on customers to adopt individual batteries. So we're looking at a couple of different work streams, but also recognizing just the mechanics of what you actually have to do to execute on some of the study work or some of the promising components of a pilot. Is probably going to take 2, 3, 4 years to execute really, really well.
Yeah, in terms of EV growth, we're definitely seeing it across our systems. Fleet electrification is huge. Amazon, large customers like that at a lot of their warehouse facilities, adding lots of charging infrastructure, having impacts on our system. Our distribution planning group pulling their hair out constantly because they're facing load forecasts that are continually pointing up and up every time there's a refresh. Some other examples, we're seeing process electrification as well. Have some large customers in Minnesota that are near where I live who are switching over their manufacturing processes from gas to electric. That's causing tens of megawatts of growth in specific areas, requiring us to look at building new substations and really upgrading a lot of the distribution infrastructure in that location. Denver Metro International Airport is another one, seeing a lot of discussions around electrification there and a lot of growth out in that area too. Folks that are familiar with Denver probably know it's located like 45 minutes to an hour east of the city. It kind of used to have nothing else located around it, and now it's exploding and there's growth everywhere and major customers coming in, major demand growth, requiring a lot of additional distribution planning and investment. So definitely something that we're seeing across our systems and again, compounded with the data center growth as well.
One of the things I think, PJ, that you mentioned that's really interesting is some customers do have the ability to shift their usage during the day. Amazon delivery vans are usually not one of them, right? They're charging overnight. You have school buses, those are usually willing to charge during the day after they've dropped the kids off. So there is some element of feasibility and realistic based on the individual type of customer.
Maybe I'll give our researchers a chance to react to anything that they've heard so far. Any thoughts? Might take a minute to turn on.
We'll try this one. I'm going to ask this question as a modeler in a modeling way, but this is not a modeling question. This really is not a modeling academic question, but I just don't know how else to express it. So my question is, should distributed energy resources be embedded in the objective function of the capacity expansion model? So in the planning process, should distributed energy resources be actually in the least cost optimization?
So I was going to get to that. I was going to maybe build up to a little bit first. But you've asked the question. I mean, that is the question for anybody who tries to model this stuff. So, and it's complex. So maybe I'll go to a challenge that I see in that first, and anybody can react to this, which is that, and I alluded to it earlier, is that, we're not planning a system where there's one decision maker. Right? If you were, this would all be really easy. Soviet style central planning. I can chart out an optimal plan for the next 5 years, 10 years, 15 years, and I can go and make each decision to invest in, customer, batteries, EVs, generation, transmission. I can do all of that optimally. And if the future was perfectly certain, and I could have a perfectly optimal plan. Of course, it's not perfectly certain. That's the problem with that model. But the problem we have in the real model is that these decisions are made by different people at different times different places, different motivations, different profit, factors, different regulators, different jurisdictions. Customer programs are, customer decisions, customer behavior is based on their own values, their own economics, their own sort of view of how they should interact with the world, which is often mediated, always really mediated through rates. So they're responding to retail rates, most of which have a huge amount of embedded costs in them, completely distorting the price signal from relative to what any economist would think was optimal. And even if the rates make an investment look like it's really optimal and valuable, they still might not do it because they can't get access to credit or capital, or they just can't be bothered. So they don't behave the way that you would want them to. Even large scale generators, they want to locate where they want to locate, which may not be where the transmission system was. So we have this multiple decision maker problem, which I think complicates the idea that you should just put this all into an optimization. And what comes out the other end is a societally optimal plan. And yet I think there is value to doing it that way, to looking at what that optimal plan might look like from a societal perspective, and seeing how close you can get to it as you try to nudge all the various different decision makers to act in an optimal way. But I don't know, utility people, what do you think about this idea? Can we just put it all into a big machine, turn the crank, and have an optimal plan come out the other side?
Paul, if you can build me a model that solves in a reasonable amount of time and can do that, I'm happy to transition. We use the Encompass model at Excel, and it's like many other capacity expansion production cost models. We have built most of our systems as copper sheet just to hopefully get it to solve in a reasonable amount of time. We've implemented some limited topology in Colorado, looking at our Piesco system. The model chokes on it quite often. We can't get it to solve. It takes multiple days, even like weeks to solve. Sometimes, I don't know if maybe, is Kestrel the name of the supercomputer at NREL? Maybe if we can get some allocated some space on that, we can start cranking through some of these model runs earlier. But compute's another issue. Like we've run historically on just like high-powered laptops and boxes on site, on premise at Excel. We're transitioning to looking at using cloud, AWS, Azure, whatever, but concerned obviously about the compute costs and making sure that we're not blowing our IT budgets, because that's another problem. But certainly I would love to optimize everything, but we have some real limitations on the modeling side right now. So the way we do it is just exogenous input. We have separate studies done. Demand response, energy efficiency, for example, we've plugged different bundles in, and I know that's probably not a perfect approach because you're homogenizing a lot of resources that are different into buckets that you're allowing the model to select from, and probably losing a lot of the granularity and the locational benefit that otherwise should be incorporated. But again, it's a compute issue, and we can't even get the model to solve if we go too detailed.
Yeah, I'm a little bit on the fence about this one because on one hand, I believe there is no place for demand side resources in capacity expansion when you're talking about resource adequacy components, and maybe to 2035, because a lot of times it gets misconstrued with, replacing a firm capacity option. And so if that's kind of the direction that we want, like do all these things instead of natural gas, I think it's a bit misleading. I do think that there may be a place for it when you're talking about deep decarbonization. And as we're marching off in this path, it's going to be more expensive. Capital is going to be constrained. It's going to be, harder to justify very large capitally intensive projects like nuclear or hydrogen or things that don't even exist yet. And I think reasonably, somebody might say, what are you doing to minimize waste in terms of the energy you deliver? So could you go out and weatherize a lot of low-income homes and partner with municipalities and low-income advocacy organizations and do that before you build a nuclear plant? That actually might be a reasonable way to analyze it. But again, I go back to that sort of decision making on the customer side. If you put something in a LED light bulbs or shade tree programs or something that isn't going to show up in capacity expansion, inherently somebody is going to think that has no value. And that might be something that is very valuable to the customer. And so it's kind of like, it depends on what it's being used for, right? If it's, you know, decarbonization, optimization, maybe, but if it's in just routine decision-making, I think we have a good way of doing it with doing capacity expansion, a suite of scenarios, and then looking at avoided cost metrics on the outside of that modeling.
I don't have anything to add.
Okay. I bet Chris does. He has a big fancy model that does all kinds of optimizations over with lots of very granular data.
Yeah, I'm biased. So, I mean, yeah, I see it as like a bit like if you're building a skyscraper, you want a blueprint and you want there to be a blueprint. And then as you start building it, you realize that it's not exactly what you need. And so you have engineers tweaking that plan as you go forward. I see it as like, you want to do as much as you can to see what the outcomes are so that you can plan against those. I don't see it as being like, these plans are the answer. They're just guideposts to say, this is what we could do, to your point of like where we could get to. I think over the long arc of time though, we're going to see a very large share of buildings having some sort of battery, some sort of solar in the distribution grid. And if we're not planning for it as we go forward, then we're going to kind of get into a pretty difficult situation if we can't model it in the objective function. And there's different ways to put it in the objective function. And, you know, it will be based on economics. And so obviously some people's decisions won't be economic, but a lot of people's will be over time. And how that interacts and how we think about market rules is like a bigger question of how those actually interact through the rate structures, as other people have said. And then the final point is, we just need to get faster at solving stuff. Like one of the things that we've been trying to do with Wisdom a lot is making it faster, making it more compact. So now we can run it on desktops, we can run it on the big computers if we want to do the whole continent. But there are ways that we can get around it. We have to have the premise that we're going to try and do it and then work backwards from that. And we don't need to get the whole way. And then make derivative models off that big master model for the different objectives that we're trying to solve for. My biased opinion.
I hope we can always, if we can one day get to exactly, you know, what you're talking about, continental scale. I mean, until we do, I guess it's been my impression that it's hard to do justice to the diversity and the potential resources that could be deployed at the customer, you know, level. You can bundle them up into supply curves of kind of alike resources, but some of them are mutually exclusive. I can either put this kind of light bulb in or that kind of light bulb in, not both. So it's hard. A lot of your decisions that you make about the demand side portfolio have an equity component in addition to an economic optimality component. So it always felt to me like you need a separate process where you go and sort through all of those really detailed, you know, supply, you know, curves, all the various measures, and, you know, put together a portfolio that meets all of the objectives for a demand side portfolio. I wonder if anyone else had any thoughts or reactions to that. Looking at you, Angie.
I think that is very eloquently said, Arne.
Paul, any responses to your question?
Well, I guess I was just kind of thinking about when slight tangent here, but if in the modeling process your model says that, you know, the least cost mix includes, you know, 500 megawatts of solar, the utility may develop themselves, they may issue an RFP for that amount of solar. How often do the RFPs include customer-sided solar as an option?
Anybody's RFPs include customer solar?
Yeah, ours do. When we put out, we don't do like where they in the mainland they do queues. For our large renewable resources for the system, we have a system need megawatts, megawatt hours. We allow grid services to also compete So we allow customer sited resources like, like an aggregator to bid into the same RFP at a lower megawatt amount.
Ours typically have a space where you can offer in a more creative solution like customer sided. We typically don't get a lot of offers there, but if we have a specific customer sided RFP or RFI, we do. I think it's pretty hard for them to compete on an apples to apples basis. The other thing for us is when we're procuring for solar, we're doing it for carbon reductions. And it is inherently way more easy through the climate registry's protocol to have a renewable energy credit associated with a utility scale solar. And that is typically not the case for distributed energy resources. It comes through as a load modifier without renewable energy certificate. So it's a little bit of an accounting problem, but that matters for the stakeholders that are asking us to do the climate registry protocol and carbon accounting.
And at Excel, we typically cut off like, I think 5 megawatts is probably the lowest threshold we have for solar that we consider in some of our RFP processes. There are some small solar requirements in our various states. So we definitely have resources smaller than that on our systems, but that's generally the approach. I think one kind of slight detour I'll make on this one, just to be a little bit provocative, is regulatory process. And again, back to the comment I was making earlier, we face huge regulatory burden, right? And that's been a big problem for ISP, is just we have so many groups focused on an integrated resource plan, a distribution system plan, a 5-year gas plan, a gas investment plan, a transmission plan, all at different times of the year, all using different load forecasts. Love what Paul was showing about the bottoms up load forecast. We have a team internally that's working on, how do we get better on bottoms up load forecasts? How do we generate that expertise internally so we're not always leaning on consultants for all this type of work? And how do we streamline the regulatory process? And thinking about like our Minnesota IRP, for example, we'll file an IRP, define size, type, and timing, and then we'll follow it up with an RFP. Why don't we just skip the initial filing and just do RFPs? I mean, we're facing load growth. We're in a period now, all of our regulators have not, or most of our regulators have not seen load growth in their lifetime or while they've been on the commissions. During my career, I've never seen load growth. Last 20, 30 years, there has not been any load growth. And all of a sudden we're facing a hockey stick. The world has changed significantly, and we have to think about how we can evolve our process and make sure that we're better prepared to grow into all of this load and adjust our systems accordingly.
To your question about customer solar, I think one of the challenges that we have with that is that many of them have an option to build solar under a net metering or even a net billing tariff. And I'm not sure why I would offer in to get paid at wholesale to an RFP when I can get paid at retail just through a net billing or net metering process. I want to talk a little bit about distribution. We haven't talked too much about that. So I'm just going to note that, one of the ways that we've incorporated some element of integrated planning in the past is through what are called a non-wires alternatives study. And we've been doing this for a long time. We've recognized that there are non-transmission, non-wires and resources that can take the place of a wires investment, and that might be lower cost for society. It's kind of a specific process where you go off and you have a specific wires investment that you're trying to defer or avoid, and you're looking for in that location what combination of demand response, customer generation, energy efficiency, et cetera, can I gather to provide the same services that the wires would provide. And having been involved in a number of these over the years, it always seems really difficult to find that combination, that magic, portfolio of demand side resources, because you put the wire in place and it's kind of set it and forget it. And every demand side portfolio requires a whole bunch of management and a lot of process and a lot of just transaction costs to get there. And there's timing issues and performance issues. And it always seems really difficult. Is there a better way to do it? Is there, how can we, we know we're putting a lot of stuff at the customer premise, is there a better way to do this besides kind of a non-wire alternative? And maybe, Paul, I'll be a little bit provocative. I noticed in your LA 100 study, you were looking at a lot of customer-cited resources, and you had a curve that said, here's some stuff we can add for free. But then beyond that, it looked like it was all cost, distribution cost. If I'm adding a bunch of customer loads or customer resources, it looked like there was distribution cost associated with that as I'm bringing more and more power back up the distribution system and then distributing it out further. So maybe just a quick reaction from you, Paul, to that, or what are your thoughts on how we can do a better job of?
Well, again, I have more questions than answers on this. I mean, in LA 100, the distribution costs were actually a fairly small fraction of the total system costs. I wouldn't say they're in the noise, but they definitely were a relatively small fraction. So that didn't really seem to present as many problems as other issues. But again, what I really want to do is ask a question kind of to go in to follow up on yours, which is, so we all talk about markets being good, but one of the things that I always think is really interesting is how much easier it is to do something in vertically integrated utilities, where if you have a distribution sited resource, it can potentially provide benefits to the distribution system, the transmission system, the generation system. And one of the questions I keep coming back to is, we always talk about like value stacking for energy storage, but when you've got a distribution sited asset in a non-vertically integrated utility, are we ever actually going to be able to solve the problem of the being able to provide benefits to both the distribution company as well as the wholesale system? So I'll kind of throw it back to you.
Might be able to with contracts. Thoughts? How can we do a better job of achieving distribution savings with better customer resource planning?
Yeah, it seems like there were a couple of questions there. So thanks, Arne, for circling back to what you want us to answer. I think in terms of distribution assets, what we have seen through the integrated system plan body of work is that you're not necessarily ever going to completely obviate the need for the upgrade. You may defer it, right? So you may get a year or two from when you would have otherwise invested in it. And so it's kind of the question is the juice worth the squeeze? And I would say in where we are with materials and procurement timelines is, that's actually where you might have a lot of value in having some of these localized programs. Is it's going to take me 3 to 4 years to get a breaker or to get a GSU or to get something that I would otherwise need. And so I'm going to temporarily count on deploying this, knowing that I'm not going to totally replace that upgrade or that equipment needed, but I'm going to buy myself some time.
Yeah, so similar to Angie, I don't have a solution, but just more to add, like, what was the solution? But like an actual distribution asset provides a step change in capacity, whereas an NWA needs to be sized very appropriately, and it's going to be a 5-year, I mean, maybe up to 10-year investment. But I mean, who can really say the distribution forecast is like perfectly clear? I mean, our crystal ball isn't that good. Yeah. So I think that's the challenge, is like, how, maybe you can defer for 5 years and maybe it'll perform. There's going to be a lot of doubts as you go through that process. Yeah, I don't know. It seems it's more valuable as a deferral than as an actual replacement.
Just quick addition for me. So again, we file distribution system plans, integrated distribution plans in various jurisdictions. We've looked at NWAs. We have prescribed NWA process in many of our states, and the NWAs we have considered, typically I think there's around 15 in each plan. We have not been able to pursue, I think, of the 15, one is deemed feasible, and then it's potentially not cost effective. So we're just not really seeing a whole lot of success on the NWA front at this point.
So Chris wants to comment on that as well, but while he's doing that, I would invite people to come up to the mics if you have questions that have been spurred by any of this discussion.
Yeah, it's really quick. I'm just going from the way we approached it was to include the distribution assets or infrastructure costs along with co-optimizing with the DERs, because there was always these increasing costs when we are adding load in the distribution grid. And so what we found was we could kind of do a normal utility plan up to the 69 kV, and then we had this co-optimization in the distribution. And where that interface happened, we looked at the cost of building out the infrastructure versus having more generation or more wires on the T side. And so it basically came up with this kind of trade-off of building out more distribution assets to take on more load, as well as backflow from PV and things like that, or building batteries in the distribution grid. So there was a big trade-off, but essentially we just kept seeing ever increasing costs in the distribution grid going forward, but it was mitigated by other choices in the utility and distribution grid itself.
So we've stolen the mic from this side of the room, so don't be shy about coming up to the front and going around. If you want to get keyed up, it will make the queuing simpler. So yeah, first question.
Quick question, Dinos Konatas. I'm a consultant working with Grid Strategies. First, I was puzzled that you said, Paul, that the distribution investment was just above the noise for the LA electrification study, and maybe I missed something about the context there. And more broadly, I was wondering, looking at all the load growth, you go to any EV conference and you hear about the gigantic demand that would be required for the charging infrastructure, but also with the data centers, there's a huge set of bottlenecks. And how long does it take from planning to end of construction to build this new substation? I was wondering, those of you who are planning those, what your assumptions are and experience would be. Thank you.
Really quickly on the LA aspect, it was basically the additional distribution costs above what would be needed anyway. I mean, you've got to do a bunch of stuff in the distribution system anyway. And then since it was a full kind of whole G&T plan, I mean, it was just the many billions of dollars worth of infrastructure needed on the generation side and the transmission side were larger than the upgrades needed on the distribution side to accommodate the distributed PV resources.
Comment on timelines.
So for a dedicated substation in our service territory, it's probably 2030 by the time we can actually get the equipment procured and construction. So I'd say right now we're sort of in the bottleneck, but we're about to enter a logjam phase, because I think what is happening is those customers, those large industrial customers, are going out and procuring the equipment that utilities need. And so there is a huge scarcity, right, in the equipment that all of us need. And so the timelines are just it's this really terrible cycle. Timelines are getting pushed out. People are getting frustrated. So they're going out and trying to find sort of tertiary or, fourth quality vendors. And then they're like, hey, we have this thing that you need. And it's like, well, why do you have it? We need it too, for all of our customers. So it's a little bit of a soapbox issue, but we're in the if you want to connect, you can probably think that they're in the 2030 timeframe is the soonest.
Yeah, I believe we're about the same at Excel. And I actually might phone a friend, 3 people behind you, who's in our transmission planning group, and have her comment on that when she gets up to the mic.
Debbie.
So the first thing I want to say is I think the DER should definitely be included in the optimization, because I think that the planning could inform programs, policies, incentives, and how you design those things. But I had a question for Chris, and my understanding is that yours is the only model that does this co-optimization of generation, transmission, and the distribution interface. And so can you say a little bit more about how the answer changes when that distribution interface co-optimization is turned on or off? Because I think that will inform whether it's important for the rest of us who don't do that now. Should we be including that in our modeling or not?
I'll try and make it brief, because there's a lot of things that change. But the couple of things that fundamentally change is, one is we see a lot more utility scale wind and solar being deployed when we have a distribution co-optimization turned on. And that's because we have more sort of load forming performance going on in the distribution grid. And when I talk about the distribution grid in our model, it's anything lower than 69 kV, even though I know that's not all distribution, but that's the way we sort of make that divide. The main thing that we lose is lots of peaking plants on the utility side as well, because we can shape the demand with the solar and batteries and demands. on the distribution side, and we can use the distribution infrastructure more efficiently with that interface. It means that you don't need as many of these massive peaking resources because there is no firming needed because the firming is taken away. But then that allows for the utilities, wind and solar to increase, because you can then make the load look more like the weather rather than less like it. So it's less human driven. And then the final thing, which is kind of really counterintuitive, over the long term, you see more and more transmission being built out in terms of megawatt miles, because you end up with these demand pockets that actually end up at some times during the day being actual supply pockets, and they need to send that somewhere else. And so the transmission system starts being used a lot more to move the distribution power around across these regions. So they're the three big things, but the main thing that I kept seeing over and over again was the fact that you do see more utility scale renewables, less firming technologies on the utility side. And you start seeing there's like a bit of a hum where there's an increase in cost, and then there's a big decrease in cost over time as well. But again, that's down more to assumptions of what the economics are and deployment rates as well.
Go ahead.
Juha Kiviluoma, VTT Finland. So I hear you talking about time of use rates, and you don't seem to be too happy about them. So why are you not working toward cost reflective rates and tariffs? So like grid costs, that would be euros per kilowatt rather than euros per kilowatt hour, having scarcity pricing, having wholesale prices and so forth. I understand it's probably not an easy sell. Maybe there needs to be some insurances or something to de-risk the customers. But in the end, that should be something that would be cheaper for the average customer and would get us closer to the optimal solution. So what is the kind of the reason, what is stopping you from going that way?
I'm sorry to ask you this. What is stopping us from what?
So
I don't think I didn't understand your question.
All right. So, I mean, when you look at the grid costs, they are mainly about euros per kilowatt. They're not caused by how much energy you put through it. So you should be having rates that reflect that. So annual fees based on your amperage or something. And then having scarcity pricing when you have a situations in the grid when you don't have enough capacity on the grid and you need somebody to be pulling back their demand, and maybe it's enough to do just broadcasting. So you're telling that now there is a situation we're going to have higher prices during these 4 hours. Those who can then can react to those prices.
Yeah, I think we generally have that. I mean, in our RTOs, you know, our rates are our rates, right? There's an energy component and a fixed component. A lot of times we get pushback from regulators on like increasing the fixed component of rates, right? They want kind of an energy usage type, you know, cost to customers. But certainly I think your point is right, as volatility in markets should drive the correct behavior. Right. I think that's kind of the point you're making. And certainly, like, I think the challenge we faced over the last number of years is like natural gas prices are really low in the United States. You know, in Europe, it's a different story, but we have really low gas prices that pushes market prices down. So in MISO specifically, like the region that my utility operates in, the market prices are not very volatile. There just isn't a whole lot of scarcity events such that LMPs get driven up to a really high level and can help justify some of the demand response or use limited type resources. So I think that's the challenge we face potentially.
Right. I also meant scarcity in the grid. So in the distribution grid, when you have the 1% of the time, then you actually might have an event in the grid. There is a bottleneck.
Sure. So you're talking about like a distribution system operator type setup. Yeah, we don't have that construct set up right now. You know, I think certainly something we could move towards at Xcel, and I think at a lot of other utilities like DERMS is a hot topic, and we don't really have an implemented DERMS solution at this point. So we don't really have that capability. It's going to require a lot of additional IT infrastructure investment. So I think fair point, something we'd like to move towards, but we're on the way there.
There's a great series of papers sponsored by a wise and forward-looking group called ESIG
on rate designs for the energy transition. So there's 5 or 6 of them if you're not familiar with them. They're really good. Lots of ideas. I think there are just a lot of regulatory barriers in the United States, largely around customer acceptability, customer knowledge, and equity considerations. But I think that is something that we're trying to move toward, but not very successfully.
Yeah, I would say just dynamic pricing signals in general. You know, for us, we need that customer information system. We need the metering infrastructure and the communication. And our DERMS platform and ADMS will go live in December. And so it needs some robust testing as well. So I'd put it in the 4 to 5 year timeframe, you know, but something that we can strive toward.
Thanks. Next question.
Thanks, Madeline Balshin, as PJ mentioned, I'm with him at Excel Energy in regional transmission strategy. My question was first sort of, I thought of it thinking of what you mentioned, Paul, with respect to the challenge for the modeling and understanding tariff implications and policy implications on how we should be planning the grid. And then Angie, you mentioned how complicated integrated system planning is even for someone within the utility with years of experience. And so it's also a little bit related to what you just said, Arne, about the fact that ESIG is producing papers on rate structures and stuff. But I guess the thought is, could we not switch the thinking to like, okay, the regulator gives new tariffs or new constraints, and then we plan to fit it, as opposed to how could utilities and other players conceive and do the research behind what are the implications of various tariff changes or various new policies that might want to be constructed. And then the research community and or the utility does various scenario modeling informing the regulators. If you want to make this policy change, this will be the cost in dollars, in equity considerations, in the ability to meet your carbon reduction goals. I guess what's the impediments to actually flipping that sort of historical paradigm?
I think she said you, Paul.
I have no idea. I mean, one of the things that has always bothered me about these types of panels, these sessions, is we kind of keep saying the same things over and over again about the need for rate reform and new tariff design. And yeah, we do. And it keeps coming back to, we don't want to allow our grandmom to freeze at night. And it's like, well, no, we won't do that. Stop saying that. Stop talking about grandmothers freezing. We're not going to do that. We're going to establish basic rates that will allow for equity, but we're going to do something more sophisticated. I mean, we've had wholesale markets now for 20 years, and yet we're not exposing anybody to market prices. I mean, we did it on the supply side. We've done nothing on the demand side, and we have to do that. Otherwise, we're probably not going to be able to do this whole decarbonization thing. So I think we just have to get over the whole grandmother freezing at dark thing, make sure that we have, take care of establishing lifeline rates or whatever that we know how to do, and let, quite frankly, people in this room, people with money, be exposed to market forces so that we have a more efficient build out. So I know I'm not answering your question. I just get frustrated by our lack of progress in rate design.
We don't even expose large, very sophisticated industrial customers to wholesale market prices in electricity. I mean, these are people that know exactly how to hedge their gas exposure.
So how long did it take between like the creation of Uber until millions of people were using Uber? It didn't take very long.
Mm-hmm.
So some industries are able to do this. I mean, the transportation system, it's this multi-trillion-dollar thing. Well, we made a radical change to the transportation system. I don't know why we can't do at least something on the electric side. And again, it's different, I understand that, but can't we at least try?
I have a little different 180-degree opposite view as a utility that is accountable for serving reliability and, having some experience of what happens when you don't do that. It was 117 degrees in September of this year in Phoenix. If we ask people to do demand response, we're inherently asking them to sacrifice their comfort. So I almost think part of the issue is just mistrust, right? That each individual utility has their mission that they must be accountable to customers and deliver what they say they're going to deliver. But it's also individual to, the load that I serve in Phoenix is much, much different than New York or Rhode Island, right? And so what works in one area of the country isn't necessarily going to be totally applicable. And we get interveners that are like, no, you could do this. Let's be aspirational. Let's move. And we believe we should do that, but we can't lose sight of grandmas that not only freeze, but that roast, right? That reliable electricity is something that we believe we are accountable to, right? And that if something happens and people do die, they're not going to look at NREL, they're not going to look at ESIG, they're going to look at the utility that they're paying their bills to. All right, I'm tired, I'm a little spicy today, I'm orangey.
All right, we have time for one last question.
Brian Palmtier from NREL. I feel like it was a tough place to follow, but I wanted to quickly offer a further answer to Paul's question, and then I think there's a related question in the panel that gets embedded into it. And so that was the question around, like, should we be including distributed resources in our overall system planning objective? And I think the answer is probably yes. And so, like, simplistically now, maybe we're taking that all primarily as an input and move from there. But it seems like something, we actually did see this a little bit in LA 100, that we probably need to capture both, because some of the value streams on the local side, I think Angie kind of alluded to some of these, that customers see won't necessarily ever be captured in those larger scale models. But there can be, particularly as we start to look at future scenarios with reductions in within city generation and other technologies. Hey, wait, maybe we do need to cite some more of these resources on the distribution side driven by system needs. And I think in general, there's actually three pieces there, right? One is the idea is, what is a customer going to need on their own? Can we capture the values from other streams so that they can see potentially higher values there? What does the system need? But then the one piece, and this gets at my question, is what about the distribution system too? It's fairly easy to quickly jump to thinking about the customer side and the bulk side, but these, even the 5 megawatt plants we're here, those are often connected to the distribution system, maybe up to 10 and possibly beyond, depending on how you define distribution. And it seems like those are another space where maybe it's three sources: customer adoption, what the distribution side thinks they want, plus what the system side needs. And so that gets to my question, which is, within these integrated planning processes that folks are seeing, to what extent and how are we capturing that kind of distribution-driven resource adoption that's not customer, but by the system? Just running it to what extent that may be seen today.
I'll bite the bullet and go first. So I think this gets back a little bit. I mentioned earlier, we're working on a bottoms-up load forecasting, and Paul kind of presented. I think that's super important. And again, it's not just a sequential planning process anymore. I think very much it's iterative. And if we can get a top-down forecast, we're feeding into the generation plan, bottoms-up that matches, it's feeding into the distribution planning process, and then we can plug that into SIME, our distribution planning model. We can look at, okay, here's our distribution system. Here are where all the costly upgrades are going to be, what NWA, demand response, energy efficiency alternatives are there. Then we can feed that back into the capacity expansion, higher level generation planning process. So I think it needs to be iterative. The earlier session, I think, was really good in saying there's never going to be a model that just solves it all. I would love an easy button, but it's not there. So getting data transferable between models is really important. That's something we're focused on at Excel. We have a universal data platform project that we're working on using Databricks, trying to pull in. We have hundreds of disparate systems with data in it, GIS, SAP, Pi. I mean, there's systems everywhere and data's all over the place. Can we clean it up? Can we spend less of our time, working on data cleanup and more of our time on modeling? So that would be my blah answer for that one.
I actually think, so some in front of the meter applications of connections on the 12 kV system. help in a few areas. One is just timelines, right? If interconnections and transmission queues are preventing us from connecting bulk system quickly, then there's something to be said about what can you do locally. That's probably limited to storage. Unless I can get the renewable energy credits for customer-sided solar, then it's probably limited to storage. I also think, that's going to take a bite out of it, right? That's not like, think about when we're talking about load growth, we're not talking about customers that are 100 megawatts connected to the 12 kV system. These are really large customers that you essentially have to rebuild another system for. And so, yeah, there's a place for it. It can maybe take a piece of it, and it can maybe help with some NIMBYism when you're citing infrastructure that's not in your service territory. But we also have to be realistic about what it can solve.
Well, thank you, everyone. We've kept everyone from their lunch, but I think it's a testament to the quality of the panel that most of the room has stayed and is still listening eagerly. So let's thank our panelists.